Hello everyone, very good morning to all of you. How are you all? So I hope every one of you is doing absolutely fantastic. This is your chemistry expert Sanjay sir, and today we will be dealing with very important topic, very important chapter for your JEE Main second attempt, and I find JEE Mains or JEE Advanced. This chapter inorganic chemistry, the chapter coordination compound is the most weighted chapter in all aspect. So guys, we are gonna to finish its theory, concepts, and a bit of practice part in today's session. And in the description itself, there is a class link, which is a special class we are going to organize on Unacademy app, which is absolutely free to all of you. Please go and click on that class and enroll yourself for free so that you can solve some 50 or even more number of very amazing questions which are highly probable question to appear in your second shift, along with some advanced level problems. Also, there's one more thing, that if you face any kind of doubts or any kind of confusion is there's a facility that you can directly ping to us, you can directly talk to us by simply raising your hand. These all facilities are available only on the Unacademy application. So let's start today's session. Today's session is coordination compound. We will deal all, this is a big chapter, actually it's a huge chapter, but we'll try to finish this chapter as quick as possible. So we don't need to understand the type of salts and how salts exist and all. We all know what is a salt. Salt is an ionic compound containing cation or anion. So if out of these cation or anion, any of the part is complex, so we can say if any of cation, anion, any of the cation, anion, or both are complex, these salts are called as complex salts, and the complex salts are also called as coordination compounds. They are also called as what? Coordination compounds. So this is about the complex salts, but again there's a confusion what complex salt exactly means. And let me give you an idea, guys. Let me give you an idea. So let us suppose I'm conducting a reaction, and a reaction between what should I say, let's say cobalt chloride is one of the substance we right now, let us say ferric chloride is one of the substance, and we have KCN with us. Okay, and this is 6 KCN we are using. So guys, the reaction occurs in such a way between these two that there is something which has been formed. There is something which has been formed. This something is actually so guys, if I talk about these all differently aqueous solution, so basically the available number of ions here, the available ions over here are, if we are talking about the aqueous iron chloride and ferric chloride, the available ions are Fe2 positive and Cl negative, also in the same K positive and Cn negative. But right after this reaction we get a very different compound which is iron, and which is K4 Fe Cn6, not K4, it is K3 Fe Cn6 plus 3K Cl. So this whole substance gives K positive ion, Cl negative ion, and a very gigantic complicated ion with 3 negative charge. But the important part is we are not getting any of iron 3 plus is not available, cyanide ion is not available in its aqueous solution, and in fact these are also aqueous. So please have a look on this reaction, and then you will understand what is the meaning of a complex salt. A very different identity of a salt, a very unique kind of salt in which you cannot get all the what should I say, constituent atoms or ions all together in the aqueous solution. Like the way we see in normal salts, we call them normal salts, simple salts, double salts, where we receive all the ions from which a salt has been composed of. But here you cannot get all the ion tests, and that is why we call them very separated and different type of salt called as complex. So that's one of the definition, and it's in an introductory part I explained to all of you. Now let me tell you some of the very important part related to the same thing. So earlier I was using one example which was K3FeCN6. So using this example, you can identify what is the meaning of all individual terms which you are using. Number one is called as coordination entity. So whatever you are writing in this square bracket, whatever it is capped inside the square bracket where a central atom is there, ligands are there, and formation of coordinate bond takes place, this is called as coordination sphere. Something which is present outside, okay, something which is present outside of this complex, which is ionizable actually, is also is called as ionization. Ionization or ionizable sphere. So guys, here you can see this iron 3 positive as an ion called as central atom or ion. We also have some kind of an ions over here, cyanide ions, which are forming some sort of bond over here, are called as ligands. And then oxidation state and coordination number you can easily find out. How? Sir, oxidation state. How do we find out the oxidation state? So whoever we have to find out, we'll put a X value for that. We'll assume X as that. Potassium always has a positive 1 in its combined state. It is X minus 6 is equals to 0. X comes up as positive 3. So positive 3 is called as the oxidation state. Now talking about the coordination number. Coordination number is the number of covalent bond, number of coordinate bond formed by the ligands with central atom. Central atom is iron. Cyanide are making a coordinate bond with iron. One cyanide is making one coordinate bond. 6 cyanide will make 6 coordinate bond. So coordination number bond will become 6, which is equals to the number of coordinate bond. And which coordinate bond are we talking about? Between the metal atom or ion and ligands. So just have a look on what the important definitions and terminologies we use for coordination compounds, and then we'll move forward. These are some set of very important terms we use: coordination sphere, coordination entity, central atom ion, ligands, coordination number, oxidation number. But again, there's a doubt that how are these gonna to be, how are these not getting separated in terms of ions when they are dissolved in water? What is the bond which is keeping them alive and together, which is not letting them reveal their identity of individual atoms and ions? So what is this? Let us talk about. So I'll give you a brief. Let us pick the same example so that we'll become more confident about what we are exactly doing. Let us take the example K3FeCN6. How this looks alike exactly. So guys, there are like 3K positive, as we all know. 3K positive. Let us suppose if I am dissolving it in water, then 3K positive aqueous plus one more species with there. This complicated anion, we are putting it in the square bracket, contains one iron 3 plus at the center, which is surrounded by 6 cyanide ions like this, forming an octahedral geometry. See, an octahedral geometry. So guys, there are 6 cyanide ions, 1 3 positive. Overall charge will be 3 negative, and again this is also an aqueous ion. So this is how a complex ion look like. It could be cation as complex, it could be anion as complex, or sometimes we can take both as complex. Sometimes we also take both as complex, both as in cation and anion, both parts are complex, right? We just have started the things. Let us take an idea how complex compounds or coordination compound look alike, and then we'll come to know about rest of the things. So anyways, the most important part over here is formation of a coordinate bond. Formation of a coordinate bond. And where is the coordinate bond formed? Coordinate bond is formed between metal and the ligands. So this is always formed in this way, that there is a metal to which ligand is providing the electron pair, and that's how it is formed. So if metal is receiving electrons from ligand, then there is some set of basically terms that we use for metal. So guys, metal over here, central atom or central ion, this is actually central atom oblique central ion. It should always have vacant orbitals to accept the electron pair. It is also called as acceptor atom oblique ion. If I talk about the its nature, it will be working as a Lewis acid. Anything that accepts the electron pair is called as Lewis acid. Now let us talk about ligand. This L is actually called as a ligand, and there is not a single ligand in a complex. It could be 2, 3, more than that, but multiple number of ligands donate one or more number of coordinate bonds. They form coordinate bond with the central atom to form a complex. So in this way, the terms which we can use for ligand will be, it must have a complete octet along with lone pair. It should be one or more lone pair. One or more lone pair with it, and along with a complete octet also. Otherwise, it will not be able to donate it if it doesn't have a complete octet. We have acceptor. Okay, this is called as a donor atom oblique group of atoms, but only one atom donates at one time, so donor atom is fine. And then it behaves as a Lewis base. Anything that donates electron pair is called as a Lewis base. So this is about the coordinate bond conditions I told you, and this is something which we study in the coordination compound. Hopefully this part is pretty clear to all of us. Why am I telling these things to you? In order to take an idea like how are we going to proceed. So I'm giving every single definition, every single basic part of this chapter, so that you can easily digest the whole chapter in once. And this one shot is highly enough for all the students who are right now watching for JEE Mains and JEE Advanced 2025. So for all the students, they want their lecture in English. Over here we have brought up the complete syllabus, and this is a most important chapter in inorganic chemistry. Let's move forward to very important part of this chapter. We have some set of oxidation states with some of the elements belonging to 3D series. So my suggestion is that better you complete all of your 3D, 4D, 5D, 6D. You all must know about the all members. We also must know about the what possible oxidation states are there, writing their electronic configuration. This is something which is very mandatorily required in this chapter. So learning about 3D series, 4D series, 5D series. Recently I took a lecture on periodic table, but periodic classification of elements, but yes, that was for the JEE 2020 aspirant. So those who have problem in learning all the elements and their sequences and about the periodic table, they can refer that chapter. Bringing back to our topic, bringing all of you back to our topic, we have coordination numbers which are possible for a particular atom with that particular oxidation states. Like copper, if it is present in positive 1 oxidation state, will always be having 2 and 4. Okay, copper will be having what? 2 and 4. 2 and 4 is the coordination number. Copper with 2 positive will be having an oxidation state of 6 and 4, like this. Okay, silver in positive 1 oxidation state usually forms 2 coordinate bond to form a complex with coordination number 2. Gold has 2 and 4, and similarly platinum with 4, palladium with 4, magnesium with 6. I would like to mark some which are very important to all of us, and these important ones are nickel 2 positive forms 4 and 6, iron 2 positive 3, both form 6 and 6, Cobalt 2 plus and 3 plus both form 4 and 6, but 3 plus mostly gives you 6. So this is very important. So these are some set of central ions with their regular charge and oxidation state, along with how many number of coordinate bond do they form in their complexes. So it's very important part. We all must go through this list first of all before starting this chapter, because once we are in the chapter, we'll be dealing with so many compounds, and there you will find that mainly of the coordination number is being repeated. So there's like so many complexes you'll find of cobalt 3 plus, but everywhere you'll find it in octahedral geometry. That means there will be like 6 coordination number will be there. Coming next type of complexes, a very simple topic from which JEE 2024, JEE 2025 and even in previous years some of the questions have come. This is your type of complexes. A complex can be defined as two types. One of them could be homolaptic, means only single type of ligands are there. So homolaptic is one where only one kind of or one type of only one kind of ligands are present in the complex. Coming to the hetero, name itself suggests heterolaptic means there will be more than one kind of ligands are present. More than one kind of ligands are present. Then it becomes heterolaptic. Let's see one of the question came in JEE Main 2024. The question is pretty simple, says that which of the following complexes is a homolaptic. Homo, we all know what homo means. Homo means single type of ligand. So there is only one example where we can see cyanide as a single kind of ligand. In rest of the others, chlorine and ammonia. Chlorine and ammonia, chlorine and ammonia. So we also have only one example. So B is the correct answer. See how easy was that. Now I'd like to take you to the denticity of the ligands and their classification. So guys, you all know what ligands mean. Ligands are the neutral or charged species. That means they could be molecules also, neutral molecules, or they could be charged ions also, which have a donor atom and which has a lone pair, and that lone pair is donated to the central atom in the order of formation of the coordinate bond. So this is what the definition of ligands is. How are we defining, how are we classifying the ligands? We are not supposed to learn anything writing down there. Nothing is going to come in our examination as a definition. So that's why it's better that grasp the concept, try to solve the questions with me, and then become comfortable for your JEE attempt and advanced attempt. Okay. Those who are right now preparing for their boards examination, this lecture is also important to all of them, but yes, talking to their 1 or 2 line definitions that they can do by their own. Let's come back to the topic. Monodentate means they can donate one electron pair. That means they can form one coordinate bond. Okay, what I can simply say that they all can form only one coordinate bond. With whom? With central atom. These number of ions which you can see or molecules. Okay, so there could be in fact water, there could be in fact ammonia, there could be in fact pyridine. These all species can donate one lone pair at once, and that's why they can form one coordinate bond at once. They're called as monodentate. There are some examples given here. Please have a look on these examples. Bidentate. We have plenty of examples for bidentate, but a very common is called as EN, ethylene diamine. So we all must know how does ethylene diamine look like. There is a donor atom called as nitrogen, which will donate like this. Then it is connected to a carbon chain which is having an ethylene group, and that's how this appears. This is your EN, ethylene diamine. This group is called as ethylene, and 2NH2 will be diamines. So it's a very important. I am continuously watching your comments as well. So those whoever are facing any kind of doubts, do let me know. I'll help them to get their doubts clear. So that is another examples could be, this is called as O-phenanthrolene. Phenanthrolene is actually phenanthrene with 2 nitrogen atoms, and both of them are the donor atoms. So it's a bidentate. Bidentate means two basically they can donate. Okay, at once how many number of coordinate bonds they can form? 2 coordinate bonds can be formed. At once it is happening. Okay, another could be salicylato. What is the salicylato? Salicylic acid is there with this benzene ring with OH group, phenol, and then COH. So this COH is CO minus, and this becomes O negative, and this all can have 2 donor sites like this, and that's why we call it a bidentate ligand. Some more examples are there. Oxalato, acetyl acetonato. A question came on acetyl acetonato this day in 2025 itself. We'll come to that question again. Dipyridine is one of the example. Carbonate, glycinate. Glycinate is glycine, and glycine with a O negative will be a glycinato. And maybe it's not mentioned, but OX2 negative is called as oxalato. Oxalato ion is C2O4. So C2O4. So this is again a bidentate ligand. It can donate via 2 sites like this. OX2 negative is called as oxalato ion. And why am I calling them oxalato? That will very much come to know very soon, that whenever an anionic ligand is there, in order to name that ligand, we put a O at the end of this name, just like chloro, fluoro, bromo, iodo, cyano, isocyano, nitro. Anything with the negative charge will be provided with a O at the end of its name. We have tridentate. Definitely, how many number of coordinate bond will it make? Will make 3 coordinate bonds with central atom oblique ion. And the example is tripyridine. What is it? Terpyridine. This is terpyridine. We also have one example, diethylene triamine. Diethyl triamine could be NH2, 1 donor atom, then CH2, or let me write it C2H4. We have NH, we have one more C2H4, we have NH2. So this is having 3 donor atoms. So that's why we call it diene. Okay, diethylene triamine. Another example is NTA, National Test Agency. Definitely not NTA, that NTA. This is your nitrile triacetato. Nitrile triacetato. Nitrogen is connected with CH2CO group. So these all are the, this one, and this one are the donating group, and that's why it's a tridentate ligand. Tetradentate ligand could be the one where 4 number of coordinate bonds are formed at once. Take an example, triene. So triene is what? There is a group NH2 which can donate. It is connected to C2H4. One NH group is there which can donate. Another C2H4. One NH group is there which can donate. Another C2H4 and another NH2 group which can donate. So how many donor atom can you see? 4. So this is called as tetradentate ligand. That means it can donate 4 at once. Next is pentadentate. Pentadentate is one of the example is ethylene diamine tri. This is a very important term I'm using here. Triacetate. Okay, I am highlighting this part. I'm saying this is triacetate, not tetra. So its structure, how does this structure look like? Let me give you an idea. How does this structure look like? So this is ethylene. So ethylene group you all are aware of. We are just now using this ethylene term. Ethylene connected with ethylene diamine means 2 nitrogen atoms are there. See, 2 nitrogen atom. And acetate group is what? Acid, CH2COO negative. So 1 CH2COO negative. This is 2. We have another CH2COO negative 3, and just a simple hydrogen. So this structure is called as ethylene diamine triacetate, not tetra, triacetate. So it is a how many donor atoms can we see? So guys, this is 1 donor atom, this is 2 donor atom, this is 3 donor atom, 4 donor atom, 5 donor atoms. So total are 5. So it is a pentadentate ligand. Pentadentate ligand. and the name is ethylene diamine triacetate with a 3 negative charge. If it is a 4 negative charge, it becomes EDTA 4 minus, which is this hexadentate ligand, a very important one. I remember IIT JEE 2010 in my time of exam asked the same question. So I would like to know, I would like everyone to know about its structure. How does this structure look like? Same NH2 group? No. Ethylene diamine means 2 nitrogen. Tetra means this time we'll be having 4 CO group, CH2, CO negative. So like if you want to ask me where are the donor sites, so these are the donor sites: number 1, number 2, number 3, number 4, number 5, number 6. So this is a hexadentate ligand. The name of the ligand is ethylene diamine tetraacetate with a 4 negative. It's a 4 negative, then it is tetraacetate. It's 3 negative, it is triacetate. Triacetate is a pentadentate ligand, and this is a hexadentate ligand. And now believe me, this question also came in IIT JEE 2010. Let me check if the question is here or not. Maybe I didn't bring the question, no problem. So it is a 3 minus. See, 3 minus. 3 minus means it's a triacetate. Triacetate means 3 acetate ions will be donating 2 nitrogen atoms. It's a pentadentate, not hexa. We have some more categories and more classification of the ligands. Ligand is a very important part of whole coordination compound. So ligands can be further classified into 2 or 3 more categories. One of them is called as flexidentate. You know what is the meaning of flexible? I'm very much flexible. That means if there's a requirement of 1 coordinate bond to form, well, I'll make 1 coordinate bond. If there's a requirement of 2, I'll make 2. If there's a requirement of 3, I'll make 3. This kind of flexibility is present in ligands also, and then they become flexidentate ligands. Take an idea that sulfate ion. Sulfate ion right now is providing 2. So that means sulfate ion is working as a bidentate ligand now. And their sulfate ion is working as a single dentate. That means it is a monodentate here. We have a few more examples, just like nitrate ion, acetate ion, this ion. They also can work as a flexidentate ligand. Okay, take an idea that carbonate over here is working as a bidentate and carbonate over here working as a monodentate in the same complex with cobalt 3 positive. That was flexibility. Now comes ambidentate ligand. What is the meaning of that? We have a single ligand with us. In this single ligand, we have more than 1 atoms. Definitely there are more than 1 atoms. Otherwise, we cannot make any ambidentate ligand. But out of this particular ion, more than 1 atoms can donate lone pair at once. But whenever it is donated, 1 atom can only donate one lone pair and can form 1 coordinate bond with the central atom. So that means, let us take an example. So we have, this is a cyanide ion. This is a ligand. This is a ligand, okay. And this is called as a cyanide ion. This ligand is called as cyanide ion. So let us suppose I'm making a coordinate bond with metal in this way, that carbon is connected here. Carbon is directly connected here. This is written as cyano C. That means cyanide is there, or simply cyano we write it. Simply cyano we write it. But if metal is making a bond with the nitrogen with Nc minus, so nitrogen is also having the lone pair, it can also form the bond, and carbon can also form the bond simultaneously. It is called as cyano N, or we also called it isocyano. So that is the difference between flexi and ambidentate. In ambidentate, one ligand can form only 1 coordinate bond at once, but there is a possibility of 2 different atoms to donate the lone pair, just like this example. Okay, would you like to try one more example? Let me give you one more example. If metal, there is a NO2 negative is called as a nitro, or we call it nitrite ion. We call it nitrite ion. Now I'll do two things here. Number one, with metal atom, I am directly bonding it to oxygen, or let's say nitrogen. I am bounding it to. Okay, nitrogen is being bounded over here. So nitrogen is making a bond with metal over here. Then it has become what? It is called as nitro N, or we also simply call it nitro. But I take the same example, but I'll making the bond with oxygen here. Oxygen, right? Exactly the same example is there. Same ion is there, but oxygen is making the bond. It is called as nitro O, or we call it nitrite. So that's the difference, guys. Okay, that's the difference. So just try to learn it, and give me a sec. I'll be coming back, and I want you to learn all the possible examples. So just take an idea and please learn it all. I'll bring water and then I'll come back in 1 minute. Just allow me a minute, okay? Please learn all examples until then. हाँ अभी कर देता हूँ, एक सेकेंड रुको. So guys, we have received a very important call from one of the very senior player of our league, and there is an announcement for all of you. There is an announcement that there is our very important channel, JEE Nexus by Unacademy, and on this channel, on 1st of the upcoming month, which is March, we are bringing India's biggest festive, India's biggest e-revolution, which is present over there only. You don't need to go anywhere. On the home page you can find it. Go here and just simply click on notify me. Just simply click on what? Notify me. Because there will be revealing a lots of beneficial things for all of you students, and it's a very biggest event gonna to happen in a tech till now which has happened. So I would like to invite all of you in joining of this amazing event which we are bringing on 1st of the March, Arambh 2024. So let's come back to our topic and just try to learn down all these together, and then I'll be coming back in 1 minute. Yeah, so hopefully you all have covered this chapter till here, and now we move forward to the next category of ambident ligand. Okay, so let's say this is connected with sulfur, and this is a this complex compound is called as uh, thiocyanate. So this will become what? Thiocyanato, thiocyanato S, and this will become what? Thiocyanato N. N because it is connected to N, like that. है ना? This is cyanate ion. This is cyanato O, and this is cyanato N. So whatever it is, green arrow is telling us that which atom is bonded to the central atom. So that we have to pick it. Okay, these are some of the examples. And another one is also, which is ambidentate plus flexidentate. We have one more example which is not just ambidentate but also flexidentate. Like take an example. This is, I think no, this is not the one. This is just ambidentate, but ambidentate means there could be two different type of donor atom. One is this oxygen and another one is sulfur. Okay, this is called as dithioxylate ion. So which of the following is both bidentate and ambidentate? Both bidentate and ambidentate, we took an example which is your dithio. This is your example. Okay, dithioxylate ion. We have one more category of the ligands called as chelate ligand. We call it chelate ligand. Actually, this process called as chelation. But in order to I usually pronounce it chelate because I love the sound chelate and just chill. So guys, this is your just chill ligand, and just chill ligand is someone which can form a ring with the central atom. So let's say this is Mn plus one of the central ion, and this central ion is having a bond with nitrogen. CH2, nitrogen. So this is now a ring. This is now a ring, and this ring is called as chelate. This ring is called as chelate, and this process is called as chelation. Formation of a ring is called as chelation. And these type of ligands which are forming the ring are called as chelate ligands. So that is what chelate ligand means. A ligand that can form a ring structure with the central atom is called as a chelate ligand. Okay, and usually polydentate ligands are one of the example of that. So EDTA4 minus could be the example, OX2 negative could be the example, Gly negative could be the example, etc. Let's have some questions, everyone. Which of the following ligand is not a chelating? You know what is the meaning of chelating? Oxalate, OX2 negative, I recently told you about. Glycinate is Gly negative, I told you about. EDTA4 minus is also a ring formation taking place, because every polydentate is a every polydentate ligand is a chelating ligand. But talking about pyridine, pyridine is a monodentate. Yeah, pyridine might be having a ring by itself, but there is no ring between the donor atom and mantle atom. So what is the meaning of this chelating? Chelating ligand must have a ring, must have donor atom of ligand and central atom together as a part of ring. So there should be a presence of ligand with the donor atom as well as the central atom while we are making a chelate. Until unless central atom is a part of that ring, we cannot consider the ligand as a chelating ligand or chelating agent. Another question: if a monodentate ligand can ligand through different atoms in a different complex, it is called as. So a monodentate ligand means only one coordinate bond can be formed at once, but we have different possibilities to form the covalent bond with, like cyanide and isocyanide. Like cyanide and isocyanide. This is called as ambidentate ligand. Okay, I was talking earlier about this question which appeared in JEE 2010, and I also qualified the same year of IIT JEE. So I remember this question was there, but this question was not about the ligand, but rather than it was about the acid. So EDTA is ethylene diamine tetraacid acetate ion. So there is a 4 negative charge of O negative. If you add HH plus to all these, it will become tetra acetic acid. Acetic acid you have to make COH. So structure is all known to very well to us. This is C, ethylene group, diamine group, and this is acetate group. We have one more question, came in JEE Advanced 2013. So let's take an idea about this question. What does this question say? EDTA 4 minus ethylene diamine tetraacetate ion, and total number of NCO bond will be how many? First of all, let us understand the structure. Okay, this is metal ion, and to this metal ion there will be like from 6 sides they have to donate it. First of all, I would like to mark it like this, that one nitrogen is here and one nitrogen is here. They both are donating. Along with that, we have CH2COO group. Okay, so we have CH2, we have COO negative, and not just one, we have what was it? EDTA. So ethylene diamine tetraacetate. So this is CH2CO. There is one more CH2CO, one more CH2CO. So as you all can see, there could be like one from here, one from here, and similarly we have CH2CO, one from here, and CH2CO negative, one from here. So this is how, like, I have made it by my own, and there could be some other ways to basically mention this octahedral species as well, but I have made it by my own. Okay, considering so many things, but the only thing I have made it incorrect is the cobalt. It's given is cobalt, not cobalt 3 positive is here. Now guys, try to understand where can you get this NCO bond. So this is N, this is CO, this is O, this is NCO, this is O, this is NCO, this is O, this is NCO, this is O. So what I can see, one nitrogen has 4 NCO bonds. So 2 nitrogen atoms will be having how many? 8 NCO bonds. So it's that simple. How easily you can identify this structure? Tell me the correct answer, guys. Tell me the correct answer. 8 should be the correct answer. 8 is the correct answer. So basically your answer is 8. Next, we are gonna to write the IUPAC names of the coordination compound. But in order to write the IUPAC name of the coordination compound, we first of all have to understand the naming of the ligands. And there comes the ligands with positive charge. So whenever any ligand contains a positive charge, at the end of this ligand we add IUM, IUM. So this is NO, means nitrosilium. NH2, NH3 positive becomes hydrazinium ion. Let us suppose NO2 positive is there, we call it nitronium ion. EM has to be added. Okay, so anywhere we are adding EM to them. If any ligand is a neutral ligand, so guys, always remember, in the case of neutral ligand, we simply put a specific name, not their usual name. Like we don't add water there, we say aqua. We don't call it amine, we call it amine, AMMINE. Ammonia, we don't call it ammonia, we call it amine. Carbonyl, nitrosyl. Please read it out, it's very important. Oh, seems like I'm not well these days. Acetamide is this, MECONH2, let it be the donor atom nitrogen, acetamide, methylamine, it will become methanamine, methyl phosphane, and blah blah blah, and so many things. Okay, this one more thing I want to add here, not here, here I'll add it. When we talk about the negatively charged ligand, which are present in majority, because negatively charged anions will easily donate a lone pair to the central atom, and that's why they are in more number availability. We have seen only 2-3 examples in positively charged ligand. We saw a few examples in neutral as well, but we have plenty of examples in the negatively charged ligand, and these are the number of ligands which are negatively charged. Take an example of nitro, NO3 minus, nitrato, carbonato. We add an O sound at the end of this name. We add extra O over there, like chloro, fluoro, bromido, or iodido. So nowadays, like earlier it was used to call it less chlorido, iodido, fluorido. Nowadays we call it fluoro, chloro, iodo, like that. Cyanido or cyano, isocyanide or isocyano, like that. Take an idea and then we'll move forward. So these are the some set of anionic ligand where organic part is there, where we do not use any O terms. We do not call it methylo, we call it, sir, just methyl. Take an idea. This is an allylic group, ALLYL. Allylo, we can't call it, we call it simply allyl, phenyl, vinyl, like that. Okay, it's like there's a, it's okay. We have some ambidentate ligands with us. Okay, we have some ambidentate ligand with us, but as I told you, this is cyanido C, cyanido N, nitro O, and this is we already have done it. Okay, why are we putting O over here? Because it's a negatively charged. Why are we putting this hyphen and C? Because this is representing us where we are connecting this central atom with. With carbon we are adding it, with nitrogen we are adding with nitrogen we are adding it, with oxygen we are adding it, oxygen, nitrogen, like that. So that's it, guys. That was the name of ligands we have covered. Now the naming of the whole complex will come to know very soon, very easily, by following some of the set of examples, some set of rules we are following, and then I'll give you some collective examples, and then you will be very much comfortable in this whole topic. Let us start naming of the mononuclear. The meaning of mononuclear is with one central atom. Complexes which are containing with one central atom. Complexes with one central atom. So first of all, cation has to be named, then anion will be named. It's just like NaCl. So how we write it? We call it sodium chloride. So basically what we are doing is, we know that first of all we have to name the cation, and then we follow the name of an ion. Hopefully we all are getting it. Next comes this example. So here also first cation will be named, like K is called as potassium. We don't need to write tetra potassium, we'll simply write potassium. Then we'll give a gap, and then we'll name this whole species. You do not know how to name it, but you will know it very soon. It is called as hexa cyano ferrate 2. So this is something that you will also know within some time, but now the first point is simple, that first cation has to be named, followed by an ion. Number 2 point says, let's say there are more than one type of ligands and we have to name all the ligands, then we have to follow the alphabetical order. Okay, not upon the basis of di, tri or tetra, but on the basis of what is the first alphabet of this ligand. So taking you to one example, let's have this example with us: platinum, ammonia, ammonia, so many things are there with no charge on this molecule, as I can see. First you identify the oxidation state, and this is bromo, this amine. So we'll write it AMMINE, amine for ammonia. We have bromo, we have chloro, this is called as methylamine. We have methanamine, and at final we have platinum. And platinum with a how much is the oxidation state? Positive 2, written down in the Roman numeral. That's how we name it. But anyways, this rule, second rule, says that we have to follow an alphabetical order in order to write more number of ligands are present in the compound, then we have to mention in them like this. Third is, we use di, tri, tetra in order to name the multiplicity of a particular ligand, like dibromo, trichloro, and a hexamine, like that. But in case if something is repeated, like one ligand is like twice there, another ligand is also twice there, instead of writing di 2 times, we first write di, and the second time we write bis. So like bis, tris, tetrakis, pentakis, like that we have to follow. So what is the meaning of this? That we initially had chlorine which are present in 2. So how am I write it? We'll write it dichloro. But we can't write di again, so we'll write bis. And right after providing a bis, you have to also provide a bracket. And in bracket, you got to write the name of this complex species called as triphenyl phosphine. Just close the bracket and write the remaining part. This is nickel with this oxidation state positive 2. Hopefully this part is absolutely clear to all of you. I might be taking enough time for all of you, but yes, my target is to make you understand all the basics and fundamental things, because I have found it from the bottom of my heart that JEE Main examination contains so many basic things in it. And one of the questions we solved, homoleptic, heteroleptic, was like this. We could have attempted this question in just a second. So I want you people to be very much focused here. Let's come to the fourth point and fifth point. Fourth point simply says that if an ionic complex is there, we have to put 8 and some special word is used for the central atom. And that em, num will be replaced by the 8. And oxidation state should written in the common in the parenthesis that we also have now come to know. Okay. Let me give you one example. First of all, we'll have complex, cationic complex as the example. So cationic complex, this is the perfect example. Then I'll take you to one of the anionic as complex. And then I'll take you to an example where both of the parts are complex. Like this. There are 3 beautiful examples and we can learn a lot from these examples. First of all, the important part is to finding out the oxidation state. For let's say cobalt we are talking about, so this is X plus 6 times of 0 charge of ammonia, minus 3 is equals to 0, so X comes up as positive 3. 4, okay, so let us first write this name. So this is hexa, its name will be hexa amine cobalt 3. This is the name of this cationic part. Remaining is anion. We don't need to write trichloride. Anionic, we simply write it. We'll simply write it chloride rather than writing trichloride. This is how we do. First question, where cation was complex. Let's say now anion is complex. What should we do? If we are having an anion as complex, so first of all, find it out. 4 plus x minus 6 is equals to 0 and x comes up as positive 2. The oxidation state of iron is positive 2. Now to write it, we'll simply write potassium instead of writing is tetra potassium, because in ionization sphere we don't need to mention how many are there. Like trichloride we didn't use, we simply use chloride. We are not using tetra potassium, we'll simply use potassium. But in internally we have to mention everything. So we'll give it a gap because cation and anion are there. Then it will become hexa cyano. Iron will not be written there, it will be written down as ferrate with its oxidation state as positive 2. That's how we name it. Now we have one more example in which both of the parts are complexes. If both parts are complexes, usually there's a high possibility, there's a 99.99% cases where both of the central atom might be carrying a same or common oxidation state. If not, it will be provided in the question either, or it will be given like this. This is one, there could be twice, thrice, 4, like that. So we'll get an idea like what is the common oxidation state over there. But we all know cobalt and chromium in their positive 3 oxidation state forms the octahedral complexes. So there simply we can find out, we can simply put it x plus 6 times of 0 plus x minus 6 is equals to 0, and x comes up as positive 3. So both of the cobalt and chromium might be carrying a positive 3 oxidation state. Now writing down its name, start from cation first. So it will be hexa, aqua, cobalt 3. Now give it a gap, and then in the continuity only you have to write, don't use a uppercase. Hexa cyano chromate 3. This is the cation and this is the anion. Simply we have to write it straightforward, simply. Okay, there could be a gap between cation and anion, but not more than that gaps are allowed. So guys, that is the typical naming of all the complexes you learned from me. In case of any kind of doubts or confusion, the chat box is absolutely open for all of you. Do let me know if any kind of doubt you face, but please keep on liking the session, and always be present in the class when I'm teaching. Let me take you to one more example, and then we'll finish the writing down these examples, and I'll directly take you to some of the questions which have appeared previously in 2025 as well. 2025 was the king. 25, 24, 23, this chapter was the king. So many questions have come previously from these this particular chapter in these years. Let us write the name of this compound. This compound is a complex compound with a negative charge. Definitely we have to write the central atom with 8, platinate. But ammonia, bromine, chlorine, so many things are there. We'll be going alphabetically. This is nitro, this is amine. A is fine, so we'll start it from AMMINE, amine, bromo, chloro, nitro. Then simply we'll write, we are not supposed to give it any kind of gap. We'll simply write it one by one. Platinate, and this is oxidation state is actually +2. 2 or 3 is there. 2 is there. That's how we name it. Okay, you can also name it accordingly. So one more question is there for every one of you. Please try writing down the IUPAC naming. Okay, you do it by your own. It doesn't require any further help of mine, homework. And yes guys, to every one of you, let me remind one more part. Those who are right now watching and those who will be watching it later, I am conducting a special sessions of completing 50 questions along with your doubt solving, along with practice doing. Everything will be covered in that session. The session is tomorrow 11 AM, 19th of February, 11 AM on Unacademy application. The link is given in the description itself. Please go and enroll yourself in that class. We'll enjoy a lot. We'll do practicing of this whole chapter, and we'll also come to know about doubt discussions and all what you face throughout this theory and that practice session. Yes, one more thing, the 50 questions sheet is also given in in that, and Telegram link is also there where you can stay updated about our upcoming lectures, these sessions and practice sessions and practice questions. Please attempt that. Please do that DPP, daily practice problem, and that will be making you very much comfortable in this whole chapter. We have this question. We are now moving forward and we'll reach out to the next question, and this is also been covered by us. So let us skip this and you can try this by your own. A very separate and very different kind of category we have, which is called as ligand, and it's a Bridget ligand. So the difference between Bridget ligand is, you will understand it in just one time. Okay, so let's say if there's an example I'm using, the example of cobalt octacarbonyl, okay, dicobalt octacarbonyl. So the structure of this compound is written as one cobalt is connected to another cobalt, and the rest are carbon monoxide, 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 carbon monoxide. I give this example just to understand what is the meaning of Bridget and terminal ligands. So guys, if I ask you how many bridged ligands are here. Bridged ligands or bridged carbonyls. How many bridged carbonyls are there? This is 1, this is 2, this is 2. If I ask you about the terminal ligands, terminal ligands will be having how many? So this is 1, 2, 3, 4, 5, 6. And one more point, let me add it over here. The number of central metal central atom bonds is how many? 1 here. So just taking an example, we can understand the meaning of bridged ligands, terminal ligands, and metal bonds and everything. So there should be one more understandability between us, that whenever a central atom is here, a central atom is here, and there is only one ligand, which is a bridged ligand. This bridged ligand doesn't share a whole electron pair, it does share one electron each. It shares its one electron each, like that. So this is the important part I wanted you people to know. How are we going to name them? That is an important part. So first of all, to all bridged ligand, you must understand to name the bridged ligand. How are we going to name the bridged ligand? We don't put them like, oh, we don't add it hydroxido, oxido, no. We simply write their name, oxide, hydroxide, like that. Hydrogen sulfide, amido. NH2 minus is called as amido because amide is different group. Nitride, carbonyl, chloride, hydride, cyanide, biphenyl phosphide, right, like that. So this is actually alkyl amide. NR3 negative has become amide. Imido, phosphido, phosphinido, that's something that you got to learn it. Now I'll take you to the name, and the namings are again very easy. And how are we gonna to name them? Let's first reach to one of the example of such. This is a let's suppose this is a symmetric complex. Why am I calling it a symmetric complex? You all can observe that the parts and the groups which are present left and right of the bridged ligand, this is the bridge, is identical. If the both parts are identical, then this is called as symmetric complex. And for symmetric complex, we can write it in two ways. One is mu oxo, we can take it at once. Mu oxo is actually oxygen. Bis means for these two, bis, pentamine, dichloro, and this ion. This is one of the way. Another way could be starting from the left, reaching to the right. Starting from left is pentamine chromium, mu chromium with its oxidation state, mu oxo, pentamine chromium with its oxidation state, and then ion. Very simple. And third could be writing down this whole part together, that mu oxo and decamine dichromium 3 ion. So this is could be the three ways, and for these three ways I would like to give you one idea, one example using this. Can we identify the nature of this compound? Is this a symmetric? Yes, platinum ammonia, platinum ammonia. Again, this is a what? Symmetric. This is also one of the symmetric complex. If we have a symmetric complex with us, we can easily write down its name. How? Let me tell you. Guys, first of all, you need to find out the oxidation state, and believe me, the oxidation state will come up as positive 2 and positive 2 only, and these two are Cl negative, and this is also Cl negative. So how we can write the name? There could be three ways. The number one naming could be, let's say I can write it mu di mu chloro di mu chloro bis. Now if once you write bis, you got to apply a bracket, and then in bracket you will be writing bis diamine platinum second, and this is the name, and then at last we'll write what? Chloride. That's it. That is one of the name. Okay, let me take you to the another way of naming. The another way of naming could be starting it from left and reaching to the right, but let me take that part first, where we'll take this thing all together. Like this is your di mu chloro then whole thing will become what? This is tetra amine di platinum with its oxidation state. Now the name of this compound complex part is over. Then we have chlorine. We'll simply write chloride. That is another way. Now we'll reach to the third way. We have the third way. In this third way, what we can do is we have the third way where we can write its name. Third way could be starting from left and reaching to the right. So starting from the left, we have diamine platinum. Second, mu. No, we'll write first di mu chloro. Then we have again one more diamine platinum. Second, this is the whole name of this, and then at last chloride. So these are the three type of naming we can do if a symmetric has been given to us. If a symmetric complex is given to us in left and right of its bridge. Let's say we do not have any symmetric. This is the most favored way, moving left to right. So this way is preferred. This is can be preferred for an unsymmetric complex also. Now we'll take you to one of the example as a practice, and then we'll wind up this particular topic and we'll reach to the next forward topic. The IUPAC name of the following complex is what? Reaching from left to the right. Now we can see this is not this is absolutely not a symmetric complex, because in amido you can see these two are different groups, and that's why we are calling it as unsymmetric complex. But we can write it. So we have pentamine cobalt 3. Actually, you will find out the oxidation state in octahedral complexes. Usually cobalt is present in +3, and it will be +3. So pentamine cobalt 3 mu amido tetra amine aqua. I think this is correct answer. B is no yaar. How? Cobaltate he wrote. Okay. Cobaltate. This is incorrect. Because of cobaltate it has become incorrect. Simply cobalt is fine, and rest everything is fine over here. D. So that was the IUPAC naming of all the complexes. And why am I going in this much depth? Because I have seen plenty number of questions coming out of this topic, and it's an important part of this chapter. So now we have another thing. How can we derive the chemical formula from the IUPAC naming? So for this, we first of all need to write down. So first of all, let me give you an idea. Let's say there is a complex called as tetra amine di chloro cobalt 3 chloride. So this is a complex name, and we got to write down its formula from its name. So how are we gonna to do that? First of all, you got to identify the central atom, which is cobalt. So just simply write it cobalt, and you arrange them alphabetically itself. So amine is there, ammonia, how many tetra, and chlorine are 2, chloro. So this is the complex. You also know the charges here. This is 3 plus, this is 0, this is -1. So using that you can identify the whole charge present on it. How? 3 plus 4 times of 0 plus 2 times of -1 is equals to This is 3 minus 2 is equals to 1. So there is a charge is positive 1 here. The charge is positive 1. And another way, we have chloride ion outside with also with minus 1 charge. Just cross multiply with the charges. You all remember in 9th standard we used to do the cross multiplication of the charges, like aluminium has positive 3, sulfate has minus 2, cross multiply, it will become Al2SO4 whole thrice, like that. So the overall formula will become what? CO NH3 whole 4 Cl2 and Cl. This is your complex now. So guys, let's solve one question on the same concept we just have studied. Which among the following will be named as dibromido bis ethylene diamine chromium 3 bromide? So we'll first of all need to know chromium. We'll write chromium. We'll add dibromido. So we'll simply write it Br2. We have bis ethylene diamine. We can simply write it En2. This complex has a coordination number of 6. And this complex has a charge of 3 plus minus 2 plus 0 is equals to positive 1. So this has a charge of positive 1. And right outside it is Br with a negative 1 charge. So just cross multiply them, right? And then you will be getting a final answer as chromium Br2 En whole twice, and we have one more Br outside of the complex. The correct answer should be B. B is the correct answer. मैं लिखूं तू आ जाए, मैं बैठ लिखूं तू आ बैठे मेरे शाने पर. So let us enjoy one song also, okay, along with this everything ongoing. See, I was talking to you about that some questions have come directly in the naming in JEE. JEE Main 2024 asked one question. Let's see how we are going to do it. We have dibromo and we'll be using bis trimethyl phosphine. So how we are writing it? Dibromo, and we don't use di actually here, and that makes it incorrect. So we have dibromo bis trimethyl phosphine platinum. Second, platinum. Second, I think this is correct. C. मेरे शाने पर सर रखे तू, मैं नींद कहूँ तू सो जाए, चल आ एक ऐसी नस्म कहूँ. JEE Main 2024, we have a question. Guys, come back to the question. The correct IUPAC name of this K2amino4, potassium, and then tetra. This is oxide actually, oxide with O, oxido, and manganate ion is there with a positive 6 oxidation state. So the correct answer should be potassium tetraoxido manganate 6. 4 is the correct answer. There we have finished the introductory part, all basics of the coordination chemistry. Now we'll take you to the first theory, the first scientist who came up with this concept of coordination numbers, and his name is Alfred Warner. You might have heard about David Warner, one of the very good cricketer and a good opening batsman, a left-handed batsman. But Alfred Warner and David Warner have nothing in common, so we can leave them apart. We'll come back to our Warner theory. Warner simply said that he gave so many, you know what, he did so many experiments based upon same compound and found a lot of conclusions out of that, and then gave a concept of primary and secondary valencies. The first of very all, guys, I would like to know you what kind of experiments were conducted by Alfred Warner. Alfred Warner had cobalt chloride with him, and he mixed it with ammonia molecules. So let us suppose this is 1 mole and I take ammonia as 3 mole. So right after that a complex was made, CO Cl3 dot 3NH3, and this complex, after addition of excess of AgNO3, silver nitrate, excess, produced no precipitate, no PPT. So what this complex was actually, this is cobalt, this is Cl3, this is NH3, whole thrice. This was the complex. So we had no separate ion over here. Okay, check out all the experiments, guys. Then he increased the number of ammonia, and he used, let's suppose, 4 moles of ammonia over here. Then he produced one compound COCl3.4NH3. There is a different way of writing this compound, because NH3, you will come to know about it, being a strong field ligand, goes and makes the bonding, replaces easily to the Cl and forms a 4Cl2, and one Cl comes out of this complex part, and the ionizable chloride can easily be precipitated in the influence of silver nitrate in excess. So there is like 1 mole AgCl white PPT. Let us check one more example as such, where we are bringing COCl3 with 5 moles of ammonia, and this is 1 mole again, and a complex will be formed which will be written down as COCl3.5NH3. But we all know that all ammonia molecules will go and make a coordinate bond with cobalt 3 positive, and 1 chlorine will be here, because octahedral complex we have to make. 2 chlorine atoms will go outside, and that means after addition of excess of silver nitrate, 2 moles of AgCl will be precipitated like that. So that's how he worked on this and reached to the conclusion. मुझे क्या चाहिए था? So guys, is this clear to all of you? How many number of basically PPTs we are getting? Hello? Yeah, man, tell me. तो देखिए काफी अजीब ये बात है कि इतनी मेहनत की वर्नर ने और इतना बड़ा रिजल्ट उसने डिक्लेयर किया, उसके बाद में भी वर्नर बहुत सारी चीजें नहीं समझा पाया. सो गाइज व्हाट एक्चुअली हैपेंड इज वर्नर out of his theory what he experimented and find out as a conclusion also made some of the postulates, and these postulates are that in coordination compound metal shows two type of valency. One of them is called as primary, another one is secondary. Primary is ionizable and usually satisfied by the negatively charged ions. These ions can be coordinatedly bonded with that or can present in ionization sphere as well or coordination sphere, anywhere they can present, they can be presented. Or then why the color is looking like this? Anyways, then secondary valence is non-ionizable and it is satisfied by the negativity. This is satisfied by the ligands only, and that's it, guys. So I'll take you to one example and we'll explain about everything. So let's see. This is one of the example. Cobalt ClH2 whole 5. Cobalt Cl2, not Cl2, just single Cl. H2O whole 5, and this is Cl2. So I would like to draw a structure from which questions may come in your upcoming exams. Using just this diagram, they ask what is the primary valency, secondary valency, number of Cl satisfying the secondary valency. This is how the question can be asked. So first of all, we all know that cobalt usually in its octahedral species is present in CO3 positive. How many number of water molecules are attached over there? 5. We have to draw the secondary valency by solid line. By coordinate bond has to be represented by solid line. This is your H2O. Then we have one more H2O. One more H2O. One more H2O. How many H2O? Okay, one Cl is also there. This is also H2O. And one is Cl. So one is Cl negative. So try to understand that there could be more number of Cl. This Cl minus is also responsible for its primary valency, because as the negative charge of this chloride ion is satisfying the positive charge of CO3 positive, making this whole complex as neutral. And we can also show two more chlorine, but they will be represented using the dotted line as it is representing the primary valency. So this dotted line, what you see, is the primary valency actually. This solid line is a secondary valency. So like that we have to basically give it, and this kind of diagram can be given in your exam, asking you what is the primary valency, secondary valency, coordination number, and how many chloride ions are satisfying the secondary valency. So how many chloride ions are satisfying the secondary valency, or that means they are coordinately bonded with the central atom. This is your Cl negative, this one only, 1. So let's say this question comes, the number of Cl negative satisfying secondary valency are how many? So the correct answer will be 1, which is this one. Right, everyone? Let's come to some questions. Okay, so let's try some quickly questions. Sir, please do all JEE PYQs. Yes, I'll do, definitely. Varun will do it. Vision under 720 will do it, and we have a session held tomorrow where we'll be bringing top 50 questions, most expected questions, including all PYQs and all very important questions of mains and advanced, where we can start practicing also. Some of the questions I also have brought up over here in this ongoing series. Let's start this question. So we have a question from JEE Main 2016. A question of JEE Main 2016, that which of the following complexes will consume more equivalent of aqueous AgNO3? Which of the following will consume more equivalent of AgNO3? So guys, we see that in water it will give no Cl negative, it gives 2Cl negative, it gives 3Cl negative, it gives no Cl negative. So as many as number of Cl negative will be there, that much number of AgCl will be precipitated out. So correct answer should be C. Got it? There we end this our Werner theory, and will take you to the Sigwick's-Ian rule. Sigwick's-Ian rule. What is this Sigwick's-Ian rule? So guys, in chemical bonding we have heard of this term called as the law of octet, that elements usually lose electron, gain electron and share electron to make their octet complete, reaching to the nearest noble gas configuration. In the similar way, the D block elements, which right now we are having their coordination compounds with as a central atom or ion, they can also lose electron, gain electron from ligands, lose electron in their oxidation state to maintain their number of electrons to their nearby electronic configuration of noble gas. So what if I tell you about the let's suppose if I consider the elements of 3D series. So elements of 3D series, you know, elements of 3D series: scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper, zinc. They all will be having the nearest noble gas. They will all be having the nearest noble gas as krypton, with an atomic number of wait argon, krypton, helium, neon, argon, krypton, xenon, radon. So this is krypton with 36. Then let us suppose there is a 4D series members are there: yttrium, zirconium, niobium, molybdenum, technetium, ruhenium, rhodium, palladium. Their nearest noble gas will be xenon with an atomic number of, add 1854. So let's say there are 5D series member is there. 5D series members are lanthanum, hafnium, thorium, tungsten, rhenium, osmium, iridium, like that. So they will be having krypton, xenon, radon. Add 32 in it, 86. So there will be 86. So effective atomic number of the complexes which will be made by 3D series will be 36. For 4D series it could be 54, and for 5D series could be 86. Very good. Now if I talk about the mathematical formula of Ian, mathematical formula of effective atomic number will be very simple: Z minus oxidation state plus 2 times of the coordination number. It's a very simple formula that we have to apply, but for Brigitte complexes this will differ, but by that time only I'll give you the perfect example. Let us solve some questions here. So let's say we have chromium CO6 here. We know the oxidation state X plus 6 times of 0 is equals to 0. X comes up as only 0. So the oxidation state of chromium will be Cr3 plus, not Cr3 plus, Cr0. So its effective atomic number will become Z. How much is the Z here? 24 minus oxidation state plus 6 times of number of electrons. 2 one coordinate bond is formed by accepting 2 electrons. So how much does it come? 36. It is coming 36, which is equals to the krypton. Let's try the same thing for iron here. This is X plus 6 times of minus 1 is equals to minus 3. X comes up as positive 3. So iron 3 positive is there. Ion will be 26 the atomic number, minus 3 plus 6 times of 2. 26 plus 9, 35 not equals to xenon, sorry, it is not equals to krypton. Getting me? But it doesn't mean that this is not stable or this doesn't exist. Compounds, the coordination compound may exist even if they do not follow the Young rule. If there is a total number of electrons which is equals to a nearest normal gas, then they are said to be more stable, but without that also they exist. So this was one of the theoretical approach given by Sigwick, knowing Sigwick's Ian effective atomic number rule like that. Let's try something for Brigitte carbonyl. So guys, as I told you once that whenever there is a Brigitte carbonyl is there, let's take the same example. Okay, first let me take this example. So guys, we must know that there is one electron each shared by two manganese atom, which is a part of both. It's like covalently shared between these two metals. So we can say that these two electrons will be counted for each one of the manganese. And I'll try to explain the effective atomic number of manganese from here. So you have manganese with 0 oxidation state. We'll simply write atomic number of manganese 24 plus 2. What is 2 coming from? Okay, first minus 0. So 0 is the oxidation state over here. Plus 2. What is this 2 electron? This is for metal-metal bond. From metal-metal bond, 2 are sharing electron. 1 is for each. 1 is being shared. Plus how many bonds are there for 1? 1, 2, 3, 4, 5. 5 into 2, which is 10. So again it is coming as 36 and equals to krypton 36, like that. But if some typical example of a Brigitte carbonyls have been given or Brigitte complex has been given, just like CO2 CO8 dicobalt tetracarbonyl. Dicobalt tetracarbonyl. So we will be having its oxidation state coming as 0, and we also know the structure: cobalt, cobalt, and then carbon monoxide, carbon monoxide, CO, 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 and CO. Check it out, guys. Check it out. Talking about the number of electrons, 2 electrons are being shared mutually. One electron is being shared like this, as I told you once by Brigitte. Rest all of them will be donating 2 electron each. Like that you have to follow. So let us suppose I'm finding the effective atomic number of one cobalt. So Z 27 minus oxidation state 0 plus from Brigitte carbonyls, how many this belongs to 2 Brigitte carbonyl with 2 electrons will be donated by 2 CO. This is from Brigitte carbonyl plus remaining one 1, 2, 3. I think 1, 2, 3 only. So 3 into 2. This is from terminal CO. Terminal CO donates complete a pair. So this will become what? 27 plus. Okay, I forgot to mention one more part. Plus we have to add 2 more. What is this 2 more for? What is this 2 more for? 2 more is coming for CO-CO bond. Now tell me how much is it coming? 72 तो नहीं आ रहा है यार. 37 कैसे आ सकता है? Actually, we have to count one only as an electron which has been shared by its own. Then I think the correct answer will come. Okay, see. There is one more way we can apply. We can identify the effective atomic number for all of the complex. So right now we try to find it for both CO atoms. If we do it for both CO atoms, then let's see how much does it come. So this will be like 2 times of 27, their atomic number, minus 0 as their oxidation state, plus 2 electrons by metal bond, plus how many bridge linked are there? 2, 4 electrons from bridged carbonyl, plus 1, 2, 3, 4, 5, 6. So 6 into 2, and these are from terminal carbon monoxide. So how much does it come, guys? Effective atomic number comes up 54 plus 16 18, that is 72. So you can find out like this, that effective atomic number per cobalt atom will be 72 by 2. 36 is your answer, and again it is equals to the 37, not 37, it will come up as 36, and that is what your answer is. And we can't add it into 2. I personally think that over here also we can't add 2. One atom is having only 1 per each, and we have to add only 1 electron. So that's why this was coming up as 35, not equals to 36. Now it is fine. We can also identify this, or we can also identify this as, just try to find out the complete one. Over here, if we do the complete one, so for two Mn atoms, if we find out the effective atomic number, how much would it come? 2 times of 25 plus number of electron transferred between these two is 2. How many number of 1, 2, 3, 4, 5, 6, 7, 8? This is 10 actually. 10 into 2 comes up as 20 plus 2 is 22. 22 plus is 70. Are yaar, how, man? Where are we missing it, yaar? What we are missing, man? 25 into 2 is 50. Okay. I am unnecessarily taking it as 24. It should be 25, and then it will come up as 26. This is correct. Actually, this is correct. It is equals to the 36 only. So this is 72. So ion of 1 Mn atom will be how much? 72 by 2, that is equals to 36. That's how we have to do it. So guys, whoever is watching, please like the session. Hopefully you all are understanding, and we have a question on this same concept, similar concept, that effective atomic number of which of the following complexes is not found out to be equals to the krypton. You know what is the atomic number of krypton? 36. And for krypton, if we talk about the krypton atom with its atomic number 36, it should belong to the 3D series only, because if anything belongs to the 4D series, that will go to the higher one, noble gas. Higher noble gas will be your xenon, radon, like that. Palladium is actually your 4D, so this will be automatically discarded. There will be have chromium, cobalt and Mn, but for them we have to check it. So chromium over here is positive 3. So for positive 3 it will be 24 minus 3 plus 6 times of 2. How much does it come? 12 minus 3, 33. This is not a correct answer. their cobalt is 27 minus 3 plus 6 times of 2, 36. 36 is correct. So I think our answer should be C. Right? Absolutely right, sir. Absolutely right. So guys, we have finished one of our very important part of this chapter called as effective atomic number, and by that now we have come to the next theory called as valence bond theory, VBT, valence bond theory. So we have some postulates of valence bond theory on which we will be understanding some kind of concepts about hybridization. So many things we will come to know, but before that we must know that the major working of valence bond theory is, valence bond theory simply mentions, just like Werner theory could not explain the proper geometry, magnetic and color properties and the optical properties as well. So that basically deficiency will be now fulfilled by VBT. We will try to do it. So Linus Pauling, you all know Linus Pauling, one of the scientists who gave the concept of electronegative, had introduced the valence bond theory, and he said that in order to make a chemical bond between the metal and ligand, which is a coordinate bond, this coordinate bond will be formed once the atomic orbitals, valence shell atomic orbitals of central atom are about to intermix to each other, providing some hybrid. They will provide some hybrid orbitals. Those hybrid orbital will overlap. Then with the overlapping will be taking place with the atomic orbitals of or molecular orbitals of the ligand. So ligand and metal, they are going to overlap to each other, giving a certain geometry to the molecule, and that's how the concept of geometry was introduced. Now I'll take you one by one to everyone, and then we'll see how the geometry is being formed. First of all, we have like two atoms are now, coordination number is 2, 2 ligands are joining there. Example has been given to us, and for 3 also example has been given to us. So let me explain this theory very easily in one case. Let us suppose the complex formed is AgCN whole twice. This is called as the cyano complex of silver, used in the refining process of silver. So guys, what is the oxidation state of silver we are getting? Ag positive. The electronic configuration of silver is all we know. Copper is 3d9, 4s2 or 4s1, 3d10. So this will become argon will become krypton. Atomic number of silver is, I guess, 47. Krypton is 36, and then it will become 3d. 10, 4s0, 4p0, like that. This is the electronic configuration actually for Ag positive. Now we all know d orbital is absolutely fulfilled. We only have s orbital available and p orbital available, because the d orbital is automatically fulfilled here. So how many are approaching 2? So one cyanide, like 2 cyanide are approaching, so we will be requiring 2 atomic orbitals of silver, which will undergo equal distribution of the energy. So they undergo hybridization, producing 2 new set of sp hybridized orbitals. Now 2 hybrid orbitals will rearrange themselves in that way that then they, like that, sp orbitals basically will try to locate themselves in such a way that they are very much different, like they are distant apart to each other, because they are containing electron. They will be containing electron coming from the cyanide, and then cyanide will be attached over here. So we can simply, instead of mentioning the lobes, I can simply write it like this is one cyanide donated over here in this way, another cyanide donated over here in this way. This is also Cn negative, this is also Cn negative. This is the complete complex we are getting with a negative charge. It's an example I'm basically giving you, but apart from this example of coordination number 2, I must say coordination number 4 and 6 are very important for our syllabus, and that has been given in our NCERT and in syllabus as well. So I will not go and wasting your time on coordination number 5, coordination number 3, coordination number 2. Let us directly jump to the coordination number 4 or 6 from here. These are some set of examples given to us. For 4 and 5 also we have some set of complexes, but how are we going to use them, that I'll let you know very soon, very easily. First of all, there are 3 examples that we all must have in our mind. 3 examples are very important in coordination number 4. The number 1 example is nickel tetracarbonyl, nickel tetrachloride, by the way, NiCl4 2 negative. So let's start it from here. That nickel has an oxidation state of positive 2 with the configuration 3D8 4s2. So this is 3D8 4s0 4p0, and this is your argon, not argon here, krypton, sorry, argon only, 18. Nickel has an atomic number of 28. This is how the electronic configuration is written. Now this is a 3D 1 2 3 4 5 6 7 and 8. This is 4s, this is 4p. So guys, how many ligands are approaching, by the way? 4 chloride ions are coming. That's why this 4s and this 4p will become available for overlapping, and they all will undergo a concept called as hybridization to redistribute the energy, and redistributed orbital will be 4 sp3 hybridized orbitals. These 4 sp3 hybridized orbital will locate themselves in such a way that this is how it will sort of look alike. You know about this. Like that. Got it, guys? So this is the structure now. So talking about the hybridization. Hybridization is sp3. Geometry for sp3 will be tetrahedral. Tetrahedral geometry will be followed. If you talk about the magnetic behavior, you can count on the number of unpaired electrons. Number of unpaired electrons are how many? 2 number of unpaired electrons are there, which makes this species as magnetic behavior of paramagnetic. Wherever you find the number of unpaired electrons, the species will become paramagnetic and it will start showing you magnetic behavior. And then since outer orbitals have been used only, not inner orbital is used, we can say it is an outer orbital complex. Because no inner orbital. What is the meaning of inner orbital? Inner orbital is actually 3D. 3D is called as inner orbital. N minus 1 orbitals are called as inner orbital, and N orbital, NS, NP, ND, these all are called as outer orbital. So that's why we are calling them inner orbital complex or outer orbital complex accordingly where the electrons are going and what configuration is used. You can also find the magnetic moment by using the formula of N into N plus 2 Bohr magneton. So this will become under root of 2 into 2 plus 2 will be root 8 Bohr magneton. That's it, guys. That is your first example in coordination number 4. Please try to understand this example, very important one. And I'll show you some of the questions came in JEE Main 2024, 2025 and even in JEE Advanced on the same concept which we are right now having. Same concept. Let's have another example. Second example will be nickel tetracyanide. In nickel tetracyanide, nickel is present in positive 2 oxidation state. Again, configuration is all of known to every one of us. Argon 4s to 3d8. So 4s0 and 3d8. 3d8, 4s0, 4p0. So guys, what usually happens, the d electrons are filled in this way. 1, 2, 3, 4, 5, 6, 7 and 8. 2 unpaired electrons were there. But since Cn negative, what we are using as a ligand, now the concept of strong field ligand has arrived. This is being a strong field ligand. So what does it do? It does a pairing of electron. It does pairing of d electrons. D electrons are now paired up. We can simply call it electrons. So now this electron will jump and go there. So this becomes 3d, 4s, 4p. This is 1, 2, 3, 4, 5, 6, 7, 8. 1 is empty. These are empty. How many number of ligands are approaching? 4. 4 cyanide ions. Now using these 4 cyanide ions, these are 4 cyanide ions. These all will go what? Redistribution of the energy under hybridization, and they will produce how many number of equivalent set of orbital? 4. So these are 4. This is dsp2. 4 dsp2 hybridized orbitals are produced. That means they will be reacting or they will be overlapping with the incoming 4 Cn negative ions. Now what we have got is hybridization. First of all, this is dsp2. Hybridization is dsp2. What is the geometry of this molecule? This is square planar. Geometry has become square planar. What if I ask you about the magnetic behavior? There is no unpaired electron. That means it has become diamagnetic in nature. Diamagnetic molecule, oblique ion. What else can you talk about now? That's it. But yeah, we see that N, S and NP orbitals are taking place along with 3D. So 3 is also used, 4 is also used. That is why we call it inner orbital complex. Inner orbital complex. That's it, guys. One more pretty good example is nickel tetracarbonyl, NiCO4 with 0 charge. Bhavishya is saying, sir, please continue PYQ series. Okay, we'll continue. Surely we'll continue. I think we have to go for the PYQ series, no problem. We'll definitely bring the PYQ series, don't worry, guys. Okay, come and check this question. We have nickel tetracarbonyl. Nickel tetracarbonyl is here. So for nickel tetracarbonyl, the first thing we have oxidation state of nickel as 0. So it will be, as an atomic number is 3d8. The configuration will become argon 18, 3d8, 4s2, 4p0 and 4d0. And since we have a strong field ligand, carbon monoxide being a strong field ligand does pairing of electrons. So these electrons will go there and will pair up near to the nucleus in 3D. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons are there. This was your 3D. This is 4s. This is 4p. How many ligands are approaching? 4. So these 4 orbitals will go under hybridization and will form 4 new set of sp3 hybridized orbitals. The complex will look like this. Nickel with a positive 0 charge will be bonded with carbonyl over here, with a bonded with carbonyl over here, with a bonded with carbonyl over here, and with a bonded with a carbonyl over here. So this is actually a tetrahedral geometry. Hybridization, no doubt, is sp3. Geometry is no doubt tetrahedral. Number of unpaired electrons are 0. The species is still magnetically, it is diamagnetic. And one more point I want to add is which electrons are used? N. So it is outer orbital complex. So even if we are using the strong field ligand, this is an outer orbital complex. Why? Because inner orbitals are completely filled, sir ji. That's why we cannot use n-1d, which is 3d. So this is something which is like a very important part of this chapter. These all 3 examples which I mentioned here, these have been asked previously as well. These 3 are very important. Please have a look on these. Try to write them by your own. And that's how we have finished with the coordination number 4. There is one thing I want to add over here, that wherever you find 4d or 5d series member, 4d or 5d series central atom or ion, there always a weak field ligand will also be taken as a strong field ligand. That is another kind of exception we have to know. Although I have come up with lots of exceptions in this chapter, there are plenty of exceptions, millions of the exceptions might be there in chemistry, but those whoever are in our syllabus and can be asked in our exam, I have come up with those kind of exceptions. We'll be revealing very soon, but now only one thing we have to revealed is this, that if you are given with let's say we are having a D8 configuration, we have what? D8 configuration. If we have a D8 configuration and this is a 4D8 or 5D8, 4D or 5D series we belong to, always a ligand will be considered as a strong field ligand only, because they have high Z effective. High Z effective of central atom or ion makes a ligand to behave like a strong field ligand itself. So that's why they will always form what? Let it be PTCl4 2 minus, PTCN4 2 minus, or PTCO4 2 minus, or no charge will be there. These all three are square planar only, because they all have D8 configuration along with strong field ligand, because every ligand will be considered as a strong field ligand, even chloride ion. That's it. Itna hi janna hai. That's what we have to know about the please come. We'll continue the PYQ series. Don't worry guys, I got your message. So we had this coordination number 4. Now I'll take you to coordination number 6. Right? I'll take you now to the coordination number 6. We have coordination number 6, in which we still have two possibilities. One of them could be sp3d2 hybridization, another one could be d2sp3 on the same basis which we have right now followed in the presence of strong field and weak field ligands. It can be possible that sp3d2 will use nd orbital, that is why we call it outer orbital complex. n-1d will be used in d2sp3, that is why it is called as inner orbital complex. Very simple part of this chapter, okay? But it's not mandatorily, it's not necessarily required that it should be a strong field ligand only or weak field ligand only. But yeah, it is generally can be said that in generally, if strong field ligand will be used, all will be paired up, D2 will be available, D2sp3 will be the configuration. If strong field ligand is not used, weak field ligand is used, will not do the pair up, all the n-1d orbital will be filled, whether partial or fully, and ns and np will be used there. The ns, np and nd will make a outer orbital complex. There is one more important part of this chapter is, for all the coordination number 6, there are some configurations where it will not matter what kind of hybridization, what kind of ligand we are bringing into, whether it is strong field ligand or weak field ligand, everywhere. Let's suppose if it's a configuration of D6, D7, D8. D8 or what? Yeah. 9. D1, D2, D3. First of all, let us take it D1, D2, D3. D1, D2, D3. It has to be filled like 1, 2, 3. Again, 2 orbitals will definitely be available, whether it is weak field ligand or strong field ligand. Because of the presence of these 2 orbitals available, n-1d, D2sp3 configuration will be there, D2sp3 hybridization will be there, and inner orbital complex will be formed every time D2sp3 will be made. These are such examples like titanium, scandium 2+, scandium 3+. But again, the configuration is D1, D2, D3. Similarly, if the configuration is D7, D8, D9, D10, D8, D9, D10, in these cases, definitely your 4 orbital will be definitely filled up, and we require 2d orbitals, sp3d2, d2sp3. In that way, every time sp3d2 will be your every time sp3d2 will be the hybridization, and let it be d8, d9, d10 configuration. So that's it. I wanted to explain that for d1, d2, d3, weak field and strong field doesn't work. It will always be d2sp3 hybridization. Inner orbital complex will be used. And as I was earlier telling you, that generally with the strong field ligand, inner orbital complex is formed, and generally with the weak field ligand, outer orbital complexes form, but not always true. This is not always true. Correct? Next. Okay, then we have one question is here, everyone. One question is here, which was asked in JEE Main 2022. The difference between the spin-only magnetic moment of C2H2O Cl2 and COH2O whole Cl3. I think one is the CO and CO2 positive is here. So CO2 positive, we will take this complex as a weak field ligand only, and configuration will be written in that way only. The atomic number is 27. So what should I write it? It will be 3D8 4S, 3D7 4S0 4P0 like that. D7 will be mentioned like this: 1, 2, 3, 4, 5, 6 and 7. So the number of unpaired electron you can get is 3. Now try the same for chromium 3 positive. Chromium has an atomic number of 24, and with 3 positive it has become 3D4 only. It was like earlier 3D3, just 3D3. I think it will become 3D3. Cobalt has 27 D7, so 3 unpaired electron were there. In 3D3 also I find 3 unpaired electron will be there. So 3D3 1, 2, 3. Again the n is equals to 3. 3D3 4S0 4P0. So the difference was asked between these two. I think A is the correct answer. Including this strong and weak field ligand. The question was asked in JEE Main 2022. And don't worry guys, those who are not right now able to identify whether the strong field ligand is given or weak field ligand, don't worry, because the segregation between strong and weak field will be revealed to you very soon in crystal field theory. When I reach to the crystal field theory, I'll explain it in very detail, okay, very much detail will come to me. Let's see another question. JEE Main 2018. I think this question has been already done from our end. NiCl4 was square planar? No, it was tetrahedral. NiCN tetrahedral? No. NiCl4 was paramagnetic? Yes. NiCO4 is tetrahedral? Yes. I think C is correct answer. Let's see how easy questions are there on the same thing that I told you. Now please read out the limitations first, and then we'll take a lunch break. Then we'll take a lunch break and then we'll reconnect soon. Okay. We have limitations of valence bond theory. First, it involves a lot of assumptions. Assumptions as in we still have no data, we have no idea upon where we have to pair up, where we don't have to pair up. First part, we assumed it by our end that sp3 hybridization must go for tetrahedral and dsp2 must go for square planar. No particular explanation behind that, to be very honest. Magnetic properties were not revealed very easily because we didn't know about strong field and weak field ligands, where to pair up, where not to pair up. It does not explain the colors in the coordination compound. We still haven't found which should be the colored, which one should not be the colored. It doesn't give any quantitative interpretation between the thermodynamic and kinetic stabilities of the coordination compound. Like we can't comment over here which one of them was more stable, NiCN4 whole 2 minus or NiCl4 whole 2 minus. Which one of them was more stable? We can't comment. We also do not know why this CuNH3 whole 2 positive is a stable complex where it is it forms an outer orbital complex. It's an outer orbital complex, but still it is stable. It also does not make exact predictions regarding to the tetrahedral and square planar structures. Why does it make outer orbital complex when the strong field ligand is being used as NS3? No idea. And it also doesn't distinguish between strong and weak field ligand and blah 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 is there. Why MnCN6 forms inner orbital complex and MnCl6 forms an outer orbital complex? This was not differentiated. So this is it guys, that is the limitation of VBT. And now we'll continue with the crystal field theory. But for crystal field theory I would require a small break from all of you. My suggestion is to please be patient and let's come back soon. We are having a small break. So please stay tuned, don't go anywhere, and just like the session. So hello guys, we are back. Hopefully you guys are back as well. So these were the limitations of valence bond theory that made us to switch to the another modern theory of coordination compounds. So how the coordination compounds are formed, on that we'll be now dealing with a new theory, and this newer theory is called as crystal field theory, CFT. And probably the most important topic of this whole chapter, because previously, in fact, if we talk about from JEE Main 2020 to JEE 2025, we have received so many good questions out of crystal field theory. Let us start it one by one. So what does crystal field theory has to say? This will give you an absolute idea that what should be the exact structure, hybridization, strong field, weak field, magnetic properties, color imparting properties. Everything will be revealed by crystal field theory. So first of all, because the unsymmetric field of ligands, the degeneracy of blah blah blah. Let me explain what happens. So guys, initially we have degenerated d orbitals. These are degenerated 5d orbitals. These are degenerated 5d orbitals. Okay. What happens when a ligand tries to approach to the central atom? These are no doubt of central atom. These are no doubt belongs to what? Central atom with a Mn positive charge. Okay. And let's suppose they are degenerated with zero energy. Once the ligand approach to them, and let us suppose all the ligands are approaching from the same uniform directions as a sphere they are approaching, so that every ligand is in the same distance with the metal atom, or then suddenly the amount of energy will be increased. This amount of energy increased is called as the spherical crystal field. This is called a spherical crystal field. Okay. Now meaning of spherical crystal field is when metal, initially only metal was there. Now we have metal under the influence of ligands, and these ligands are approaching uniformly. All the ligands are approaching uniformly. Now let us suppose I am discussing about the splitting in octahedral complex. Let us suppose if you are discussing it about the octahedral complex. If we have to split this thing in octahedral complex, then what will happen? There will be like two groups will come up over here. Two electrons, two orbitals which will be directly facing, which is dx square, y square and dz square. These orbitals will have higher energy now, and the remaining three orbitals which are non-axial orbital, dxy, dyz, dxz, they will basically reduce down with their energy. This is the energy of this is called as a barycenter. Barycenter, which is exactly representing you the energy of the spherical crystal field, where uniformly all the ligands are equidistant to the M. All of them are equidistant. But we all know this doesn't happen. This doesn't happen, and instead what happens? Splitting will take place. How? Because let us assume it's 6 ligands are approaching. Okay, we are now studying in the octahedral complex. And let us suppose I am right now the metal at the center of this whole room. Okay, this room is basically the center, and at center the central metal is placed, which is me. From all the face centers, okay, take out the example of face center 1, 2, 3, 4, 5 and 6, an octahedral will be formed in this way. 6 ligands are approaching toward the central metal atom, which is placed at the center of a cube. The orbitals which are directly facing to the ligands, are these. The one which are directly facing over here are dxy and dx square y square and dz square. They will acquire more energy and they will be shifted up now, a bit upwards. How much energy do they possess? This energy is actually this whole amount of energy. The gap between these two is called as delta O. Delta O is called as the crystal field splitting energy in octahedral complex. Crystal field splitting energy in the octahedral complex between these T2G orbital. These all are completely called as T2G orbitals, and these two are called as EG orbital, equally degenerated orbital, and they are called as triply degenerated orbital. Where G means G-rad, which is not of our concern as of now. G-rad means it's related to the symmetry of the orbitals and symmetry of the system. Leave it up behind, just simply take it T2G, EG as of now. And so how much is this energy, by the way? We all know that overall this is the amount of energy which we are right now having. This was some zero energy. This is some zero energy. Nothing was, this is the ground state actually. This is the ground state energy. Then we reach to some very center energy, the central energy. If the uniform field is being there, it's a spherical crystal field is there. And then the splitting is occurring. The splitting over there, the gap over here is this orbital has the gap of 2/5 delta O. Positive of not 2/5, it should be 3/5. 3/5 delta O. And this gap down over here is a gap of negative 2/5 delta O. This is a positive, this is a negative. Now, what is the meaning of this thing? Then we have a different kind of energy called as a crystal field stabilization energy. What do we call it? Crystal field stabilization energy, also called as CFSE. So this is calculated using a formula in the terms of delta O, which is the crystal field splitting energy in the octahedral complex. So how many number of electrons are there in EG got to be multiplied by positive ka 3/5 delta O plus as many as number of electrons are there in T2G whose energy is decreased will be multiplied by negative ka 2/5 of the delta O, and along with that we will add some number of pairing also, NP. So N is the number of pairing occurring, P is the pairing energy. This is some sort of energy which has been called as the crystal field stabilization energy. Usually this energy comes in negative. Why does it come in negative? Because as we all know, even in Bohr's theory, the stability of an atom is explained by its negative energy, negative of 13.6 Z square by N square electron volt per atom. Similar way, the energy overall for this metal and ligand complex formation should come up as negative, because higher is the negative energy, higher is it showing us the stability of the molecule, stability of the complex it is showing. So this is called as the splitting in octahedral complex. Hopefully you all have got what I tried to explain. Okay. Now what does this delta O depends upon? What is this delta O depends upon? As the charge on the central metal atom, which is also called as the oxidation state of central atom oblique central ion. So as the charge of the central atom increases, stability of the complex also increases, delta O also increases, because higher is the Z effective, higher is the attraction of electrons towards central atom. More is the interaction between the central atom as a cation and anion, which are ligands right now approaching. Higher will be the energy gap between these two. And this energy gap is also directly proportional to the stability of the complexes, because in that way more number of electrons in negative side will go in T2G and will be giving more amount of negative CFSE. Higher is the negative of crystal field stabilization energy, higher is the stability of the complex. Like that it works, okay, vice versa. So that was the first point we had. Then another point says that whether the metal is in the first or second or third row of transition element, it has higher Z effective, it increases with the increase. So basically this is trying to explain the value of delta O also depends upon, so I can write it like delta O varies like 3D series elements will have lesser than 4D, and that for 5D will be have higher. Why is it so? Because it is directly proportional to the Z effective. Simple as that. I guess both of the points have been covered over here, and the initial point is very important to explain because the rest of the theory is very easy and it can be easily depicted. So guys, if we use the weak field ligand, then less interaction, less attraction and less repulsion will take place. That's why low rise of the energy and the splitting will be lesser. Higher splitting will take place if the strong field is been there. Strong field again gets more energy of EG and lesser energy decrease in T2G, and this is called as more splitting. So how is this decided? Who decided this, that it should be a strong field ligand, it should be a weak field ligand? This has been calculated experimentally by using the term CFSE, crystal field stabilization energy. So what we did, we fixed some central atom and we fixed its coordination number, and we used different types of ligands, and the complex so formed, we applied some sort of basically visible light over there or some sort of electromagnetic radiations over there, and tried to find out the gap between these two, between EG and T2G. The gap was higher in case of carbon monoxide, cyanide, EN. They all then called as the we all called them as strong field ligand. So whatever, actually the barrier is water. Whatever it comes below water, including water, is called as weak field ligand. Whatever it comes beyond water and till here, they all are called as strong field ligand. So NC is from there to there, they all are strong field ligand. And from water continuing with water and these all, they are called as weak field ligand, right? That's it. So ligands can be arranged in a series called as the spectrochemical series, and this is the order of their strength. And what is the meaning of strength over here? Like how much splitting they can arise, they can make between EG and T2G orbital is called as the splitting. This series is called as spectrochemical series, which is kept completely experimentally driven upon the basis of the absorption of the light. Higher is the wavelength, higher is the frequency of the light absorbed there, higher is the energy, and higher is the delta O, yani octahedral splitting energy. Then we have complexes with different ligands have been tried over there. Strong field ligand generally leads to the absorption of light of higher energy, higher frequency and lesser wavelength. And weak field does in oppositely, as of lesser energy, lesser frequency and higher wavelength. That's it. That is your crystal field splitting energy is all about. Let's see one question which directly came from this theoretical data of spectrochemical series. So I would like to know how to decide it part. So guys, talking about this spectrochemical series, I heard of so many mnemonics, but none of them suited to me. I might feel myself as a poor student over here because I couldn't learn the whole spectrochemical series. But I have one thing in my mind, which is this beauty of my mind, which led me to explain that whenever I find carbon and nitrogen donors, carbon nitrogen donor atom, this is called as strong field ligand. The order will be cyanide. Okay, the most is of carbon monoxide. The most strength ligand is CO, followed by CN negative, ammonia, ethylene diamine, okay, EDTA, EN and H3DTA. And so on, like that. These all are the strong field ligand. Which one are the strong field ligands? Are the one which have carbon and nitrogen donor, and the one which are having oxygen, sulfur and sulfur, oxygen and wait, let me check it. We have oxygen donor, sulfur and halogen donors. They are regarded as weak field ligand. Their example could be water, oxalate, right? See, you can see it over here. Water, oxalate, OH negative, F negative, S negative. Hydroxide, fluoride, sulfide, then your chloride, bromide, like that. So this is the only way we can learn it. We are not supposed to rote learn down the whole complete series, but using this only we can get the idea. Now, if you want to check it out, let's take an example that came in JEE Main 2024. This question is actually of JEE Main 2024, and let me give you the answer. The correct order of the ligands arranged in the increasing field of strength. We all know that nitrogen donor are stronger, carbon donor are stronger, and cyanide will be the best. Cyanide will be the best out of these all. So this order is incorrect because of this. This order should come up as fluoride, chloride, bromide, like that. This is the order which is incorrect because of this order. We know that carbon monoxide, then comes cyanide, then comes your EN, and then comes ammonia. So it is like way far. Then we have bromine, fluoride, this order. I think this is correct. This is correct order actually. Here also we have this is incorrect actually. This order is incorrect. So I think C is the correct answer. But again, I just guessed it and I made the correct answer out of it. I just guessed it and I just made the correct answer out of it. And exactly the same thing I want from every one of you. Every one of you, I want the same thing. That's it. C is the correct answer. That's it. Now let's see another question. The complex that has highest crystal field splitting energy. So this is not, we are not gonna to find it out for every single one of them. No. We can simply identify by using the concept of ligands. We all know that higher is the splitting, higher is the strength of ligand. So delta O is directly proportional to delta. First of all, you must know that delta O is more than delta tetrahedral, is more than delta SP. So wherever the square planar complexes will be having higher crystal field splitting energy, and tetrahedral will be having relatively lesser splitting energy. But again, out of these, this forms a tetrahedral complex. This form sp3 complex, tetrahedral. So delta T or definitely lesser. Delta T is definitely lesser. Now talking about the rest one out of them, we have 5 ammonia, and we have 6 cyanide. 6 cyanide has highest. It is delta O is directly proportional. In fact, delta of anything is directly proportional to the strength of ligand. Directly proportional to the strength of ligand. The correct answer should be D. Now I intentionally took this example in order to explain you how many number of pairing we have to do, because if there is already a pairing in the normal electronic configuration, then that pairing has not to be counted. If the pairing has to be done by ligands forcefully, then the pairing has to be counted in the total crystal field stabilization energy. What I'm trying to say, let us see in the example itself. We have a D6 cation, D6 configuration, and we also have a low spin complex. That means we are using a strong field ligand. Low spin will be observed when strong field ligand will be used, all the electrons will be paired up. That's the case of using the low spin complex. Let's try this. So first of all, we have a D6 configuration. Then D6 configuration, first of all, it already has one pairing. How? Sir, 1, 2, 3, 4, 5 and 6. We have already one pairing with us. If we split this under the influence of a strong field ligand, that's why we are getting a low spin complex. All 6 electrons will be paired up like this, and none of the electrons will be remaining in the EG. This is all EG, this is all T2G. Negative of the energy will come up. If I find the crystal field stabilization energy, it will be the number of electrons multiplied by negative ka 2 by 5 into delta O plus plus how many extra pairing are there? These two are the extra pairing which has happened, which have just taken place because of the presence of strong field ligand. So 2 times of pairing will be added, and that makes this formula as the crystal field stabilization energy as 12 by 5 is 0.6, 12 by 5 negative 12 by 5 delta O plus 2p. I think B is the correct answer. So that's why I took this example. It's a very important example, and I want every one of you to know about it, how this example has been asked in exam and what to do like that. B is the correct answer. Then we have tetrahedral complexes. So in order to imagine about the tetrahedral complexes, you have to imagine yourself at the center of the room, and from the alternate pick one of the corner and then pick alternate 3 corner. What is the meaning of alternate 3 corner? None of the corners should be the next to it as in on the edge. It should be in the diagonal. So this is, let's suppose this is one of the corner. The another corner should not be this. It should not be this. It should be diagonally opposite to that. This. Correct? So more or less, if I can draw it, I would like to suggest you what is actually happening over there. We are now taking an example of a cube. Look at this cube, guys. In this cube, let us suppose this is where the central atom has been placed, Mn plus, and this is the one corner I am picking. So one corner is actually approaching from this end towards itself, central metal atom. Now another should not be placed over there, should be diagonally opposite to there. This is the one. Now next diagonally to it, it will be this. Diagonally to it will be this. We are not using this, we are not using this, and this is where they are approaching and forming a tetrahedron. This is a tetrahedron actually they are forming. Now if you basically add them, join them together, your structure will somehow look like this. This is Mn plus present at the center, and 3 things are approaching. 1, 2, 3 and 4. And as you all know, this is a tetrahedron with a bond angle of 109 degree 28 minute. That's how the appearance look alike. Hopefully I have explained it very good. Splitting will again take place. Splitting of tetrahedral species, tetrahedral complexes will be lesser than that of octahedral, because in octahedral there were only 2 orbitals which were directly facing the whole repulsion. 2 orbitals will face it, they will experience more repulsion. 3 orbital will face it, it will be equally divided. So that's why it is 2 by 3rd of that way. Another thing is, there initially were approaching 6 ligands, now it is only 4 ligands. Since 4 ligands are only approaching, repulsion has already become 2 by 3. So 2 by 3 into 2 by 3, it becomes 4 by 9 times of the delta O. So delta T, let me write this very important part, that delta T is exactly equals to 4 upon 9 times of delta O, which is very important part to know about. So that's it. This was spherical crystal field, then we had this much. The similar configurations will be used. Delta T is delta 4 by 9 times of delta O. In tetrahedral entity formation, the d orbital splitting takes place, but again lesser number of orbitals are getting the repulsion and lesser number of ligands are approaching. That makes 4 by 9 times of the delta O. And orbitals energies are not sufficiently large to forcing the pair, and thereby low spin tetrahedral configurations are rarely observed. So in basically, since the gap is not too much, as you all can see, this gap in tetrahedral is not too much, and that is the only reason for which not so many low spin complexes take place. Always higher spin complexes will take place in sp3 configuration and tetrahedral species. Let's try a few questions from here, everyone. Let's try a few questions. The values of the crystal field stabilization energies for a spin d6 metal ion in octahedral tetrahedral field respectively are. Octahedral and tetrahedral, d6 is given. Okay, so let me try this. First of all, we have d6 configuration. If I try it and strong field or weak field, what we have to convey? High spin. High spin means in the case of weak field ligand we have to take. If we take weak field ligand, electrons will remain unpaired. Unpaired electron will cause its electric effect and magnetic effect will be caused, and they are called as high spin complex. So d6, and let's say if I'm talking about the octahedral, then this will become Eg, this will become T2G. Number of electrons 1, 2, 3, 4, 5 and 6. So crystal field splitting energy will be, how many electrons can you see? 1, 2, 3, 4. So 4 times of negative of 2 by 5 delta O plus 2 times of 2 by 5 3 by 5 delta O. So this is actually 8 by 5. This is 6 by 5 to 2 by 5. So negative of 0.4 delta O is your answer. This is what we are doing in case of octahedral complex. Now I'll take you to the tetrahedral complex and let's try to find out the distribution of energy and final energy. Crystal field stabilization energy. This is d6. In d6 we have T2G will come over here. We don't write them T2G, we simply write them T2. Instead of Eg, we also write them simply E, equally degenerated orbitals. G stands for G-rad, and G-rad is only possible in the spherical complexes of octahedral, not in the tetrahedral. Tetrahedral no has a symmetry. Octahedral had that symmetry, and that's why it has been put with the value of G. This G means G-rad, but not of our use as of now. Simply move forward and fill the 6 electrons accordingly. So 1, 2, 3, 4 and 5 and 6 comes over here. So the crystal field stabilization energy for this tetrahedral complex will be how much? Number of electron over here 3 multiplied by negative of 3 by 5 delta O. This will be negative of delta T. Okay, this will be more, guys, energy, negative of 3 by 5, and this is positive of 2 by 5. Plus, how many electrons are there? 3 into positive of 2 by 5 delta of T. Now you add them and you will get the value. 9 by 5 and 6 by 5. So this will be 3 by 5. So it's negative of 0.6 delta T. And no pairing has been concerned over here. No pairing has been taken till now, because no pairing will take place in real, because D6 configuration already has one pairing. So no extra pairing has been done by the ligand side. The correct answer should be A. All well, all set, all cool? Why not, sir? A is correct. That was the question in JEE Main 2020. Now there are some set of exceptions that we have to know, because I have seen plenty of questions previously in exam. Let it be JEE Main, let it be JEE Advanced. So many questions have been asked from these notable exceptions. So please, I'm star marking these all exceptions. Read it out at once and just learn it and learn down it anywhere. Just try to write down, learn down in your mind, because this is absolutely going to be very important. And so many questions I can show you. These questions have come on the same topics which have been written down as an exception over here. Let's come to the first one. The first one simply says that higher oxidation state, positive 4 or more of central atom always forms a low spin complex. So this is saying that, take an example, we have nickel in 4 positive oxidation state. The configuration of nickel 4 positive will be, the atomic number is 28. 3d8 4s2, so this is argon. 3d6 4s, 3d6 4s 0, 4p 0, like that. So they all will be paired up over here, because even with this high Z effective or high oxidation state, we'll have high Z effective, which makes even fluoride is a strong field ligand, and then we will fill all of them 1 2 3 4 5 6 like that. 2 orbitals of 3d will be remaining unfilled. This is 4s, this is 4p, and the correct hybridization will become what? D2sp3. Got it? Similarly, one more thing is there. If you see cobalt 3 positive, cobalt with 3 positive has a very strong Z effective. Cobalt with 3 positive has a very strong Z effective, and since it has a higher Z effective, even oxygen donor atom or oxygen donor ligands like water, oxalate, they also behave as a strong field ligand. So no doubt they will be bonded with cobalt 3 positive, giving you. So like if I give you an example, that CO H2O whole 6 3 positive, the hybridization over here will be D2sp3, inner orbital complex will be formed. We know that water is a weak field ligand, but no, over here water itself will behave as a strong field ligand. Let's see, let's check another example. Ammonia is also has a dual nature. The duality of ammonia can be explained in terms of weak or low oxidation state or lesser Z effective, wherever the cation will be having a lesser Z effective. In lesser Z effective, you can identify manganese, iron, and cobalt 2 positive can show you the complexes of outer field complexes. So like let's take an example of Mn. H2O whole 6. No, not H2O, sorry, NH3. Two plus. So ammonia will be working as a weak field ligand there. If ammonia works as a weak field ligand, then manganese 2 positive will be having a configuration of manganese is what? D6, D5, 4s0, 4p0, and basically D5 configuration will filled in this way. 1 electron each, 5 electrons are there. No pairing will take place, and the configuration will be, the hybridization will become what? Outer orbital complex sp3d2. This is what I'm trying to explain. And fourth is for all 4d and 5d that we have learned even in VBT, valence bond theory itself, that all the ligands behave as a central strong field ligand if the central atom or ion belongs to 4d or 5d series. So these are some sort of notable exceptions that are very much known, that are very much useful, and very frequently have been asked in your JEE Mains and Advanced journey, and previously in some of the years they have been seen very vastly, and that's why I have come up with these all exceptions. These 4 exceptions must be known to all of you on your fingertips. Right after completion of crystal field theory, we have its application. So coordination compounds, coloring coordination compound is nothing but the application of CFT. This application of CFT, crystal field theory. So guys, it's very simple that whenever there is an unpaired electron present, whenever there is like 1 or more unpaired electrons are present in 3D, and in 3D this has been provided with a visible light and one of the radiation of visible light. So you know what is this visible light I'm talking about? This visible light is actually 400 nanometer to 750 nanometer, or 4000 angstrom to 7500 angstrom. One of the wavelength of this light will be absorbed So this is our complex, and this complex absorbed. This is called as the absorbed light, and the remaining light will produce some color. This is called as the complementary color. Will give you what? Complementary, or complementary oblique we call it observed color, observed or complementary color of this. So what is this meaning? We'll tell you, but first let us look at the mechanism of color imparting tendency by coordination compound. So this is a coordination compound. Let's say this is a purple color compound, which is a very important compound, purple violet color, very important compound given in CRT itself. It has a configuration of 3d1. Then one electron, after absorbing the energy, first it is undergoing splitting, and this is absorbing the energy. This energy which it is absorbing is of blue and green region. So blue green region, and this gives you violet color. This is some absorbed energy. This is the absorbed amount of energy. Makes a transition. The electron goes in the up state, and then the remaining energy will be looking you. So the energy it accepts absorbs is in greenish bluish region, and then finally this is the mechanism called as DD transition, and the color of DD transition is violet. So what we have learned so far from here, what we have learned so far is all the complexes in which there is one or more unpaired electron, they will show you color because of the mechanism called as DD transition. What is the DD transition? We already had a separated two layers of the energies in the terms of d orbital. One of them is called as EG, equally degenerated, another is called as triply degenerated. The triply degenerated could have lesser value of energy in octahedral complexes, and EG might be having higher energy. The energy gap between these two lies in the visible region. So they always absorbs the light of visible region, and then they give you, reflect you the remaining amount of light called as the complementary color. So if you want to know about what complementary color will be getting after absorbing a particular wavelength of the light, I'll tell you that. And for that I have a beautiful pizza wheel with us. How many slices of a pizza do you see in a pizza, medium size pizza? We see 6. We always see 6, but one of unevenly 6 pizza slices are there. So let us put their names as VBGYOR, VBGYOR. Violet and indigo I'm taking all as like same only, violet and indigo, VBGYOR. So VBGYOR has VBGYOR. So let us suppose that somebody absorbs orange color. So this is absorbed light. Absorbed light is orange color light. Although the light is always white light. Light is always white light. Now this white light may come from the sun, or coming from the any source of monochromatic source of the light, or anywhere it is coming from. This light will have a particular partition of this will be absorbed. So white light is imparted, out of which orange light has been absorbed. So this blue will be your visible color. This is your absorbed color. Blue will become the visible color. Check it out, guys. Isn't it easy, guys? So let us suppose somewhere green light has been absorbed. Green light has been absorbed, and the question is asked that which color will it give? It will give you red color. Will be visible to us. Red color will be visible to us. This is called as it's a pizza basically, and its pizza is actually giving us the what color will be shown by complex if it absorbs the light of a particular color. Let's try this question. So that is it in our syllabus. Actually, you might be wondering, guys, there are some more examples like this. Let us take this example. We have MnO4 negative, or let us suppose this is KMnO4, one of the complex, K2MnO4, K2Cr2O7, K2CrO4. So first of all, let us apply this question. Then we'll identify what is being given over there. Identify the complex which expected to be colored. So we have titanium 4 plus, which has configuration of argon 3d0, cadmium 2 positive, krypton 36, 4d0, vanadium, scanner vanadium 23, so plus 3 is there. Oh, it has 3d, so scanner vanadium 3d3 4s2 3d2, 2 unpaired electrons are there. And at last we have scandium with a 3 positive, we'll be having argon 3d0. The correct answer should be C. C is the example with unpaired electron. So this will be showing electron color due to DD transition. But what about these examples what I am bringing over here? This is actually, you will get this compound KMnO4 is purple in color. This K2MnO4 is green in color, manganate ion. This is orange crystals and orange in color, in fact it's aqueous solution, and this is yellow in color. So if I consider all of these, I'll find this is manganese 7 plus, this is manganese 6 plus, this is chromium 6 plus, and this is chromium 6 plus. But will you believe me, these all have no unpaired electrons. So guys, this is the answer behind that, and this is what we have to know. Actually, the proper explanation behind the charge transfer is not in our syllabus, not even in NCERT, not even in our JEE Mains and Advanced syllabus. This is a part of masters. If you do the masters in chemistry, and you will be eligible for doing this, is called as charge transfer. Okay, good. So what I'll say, this is due to charge transfer. This color is due to what? Charge transfer. But what doesn't happen over here? No DD transition takes place. It's all because of the charge transfer. It could be ligand to metal charge transfer, metal to ligand charge transfer. This is called as the another reason behind the color. And that's it for the color, guys. This is what we have to know about the color imparting properties of complexes. Let's see one more question over here. The correct order of the energy absorption for the metal complexes is, the correct order of the energy of the absorption for this will be, so I think higher is the energy gap between the EG and T2G orbital. For all these octahedral complexes, higher will be the amount of energy gap, higher will be the energy of absorption required. So I think this, the En has higher or NH3, I think En is higher. So I think this should be A, B and C. Actually, this is the order of delta O. If it is the order of delta O, it will also be an order of energy absorbed. So CBA, A is the correct answer. As usual. All well, all set? Yes sir, why not? Then what are the limitations of this theory? This theory assumes ligands to be point charges. According to this, the halide ion should have strong field, should be strong field ligand, but they are not. So the theory follows that anionic ligand should exert greatest splitting, but anionic ligand actually are found on the lower end of the spectrochemical series like halide ions, and it doesn't take into account the covalent character because it doesn't explain you the coordinate bond formation. It only explains us the ionic interaction between the central atom ion, metal atom or ion, and the ligand with negative charge, and central atom with the positive charge. So it shows you on. So that was the limitations of this theory, and with that now we have come to the next question. So before this question, I would like to tell you one part. I would like to show you the splitting in crystal. I would like to show you the splitting in square planar complex. The splitting in square planar complexes. So first of all, we must know what square planar complex does, where the ligands are approaching from. This is a cubical box, by the way, and we have central atom placed over here. And let us suppose this is x direction. Array, what's wrong here? क्या बकवास है, क्या है ये? Okay, I'll come back. So wherever I was trying to explain you about splitting in square planar complexes. So how does it work? First of all, let me take you to one example that from where these things are approaching, these ligands are coming and central metal is placed, and we always take this thing considering the electrostatic model, the ionic approach, and this ionic approach requires a solid state. Solid state was one of the very important chapter from advanced point of view, but now in JEE Mains it has been removed. But anyways, we'll cover it in the times of advanced. There is a central atom called as Mn plus, in which from x and y directions the ligands are approaching. So one of the ligand is coming from this side, one of the ligand is coming from this side, and this is, let's say, minus x, this is, let's say, plus x. Then comes from let's say this is from positive y side, from there also it is coming, and from there also it is coming, and this is your minus y. So what I'm trying to explain is, this is a cube, and from positive x and y axis total 4 ligands are now approaching. So what I personally find is dz square now is supposed to have the lesser amount of energy. Okay, so let's say if we were already having the 6 electrons over here, 5 degenerated orbitals in spherical field. So this is your spherical crystal field in which all the ligands are symmetrically surrounding all the central atom and all the orbitals. Then we came to know that there is a splitting takes place usually in EG and T2G. This is your T2G splitting and this is your EG. So basically this T2G and EG, which were dx square y square dz square dxy yz and xz, they all will further be splitted in this way. The most energy will be acquired by, what do you think, which one will be having highest energy? The highest energy will be of dx square y square, because from x and y the 4 orbitals are approaching, 4 ligands are approaching, and its energy goes a bit down over there. This is your dz square. Now we were expecting that dz square should have the least amount of energy, but no. How does the dz square look like? Like this. So the electron density is not just in z direction. This is a dz square orbital, but also in xy plane. The ring is actually in xy plane. So that's why it also feels an experience. It also experiences the repulsion. And now wherever the x and y is there, that will acquiring more energy. Then comes the energy of dxy, and then finally comes 2 orbitals with xz, yz. So this is how the splitting of energy takes place in square planar geometry. Okay, this is again our barycenter. This is nothing but the barycenter. Now let's come to this question, which was exactly the explanation. The explanation has been already given over in square planar complexes, and we also must know one fact, that the delta of square planar is even higher, because as we all see that all the 4 orbitals are now, four lobes, 2 orbitals are strictly facing 4 ligands directly, and the delta of sp is even more than the delta O. And how much is it? Delta of sp is exactly 130%. So 1.3 times of delta O. So overall what we can say that delta Sp is highest, followed by delta O and followed by delta of tetrahedral. So if any complex is being given to you with these three kind of things, one of them is square planar, another is tetrahedral, then more stability will also be given by the square planar because of its higher crystal field stabilization energy and crystal field splitting energy as well. So that's it. Let's come to the topic. A complete removal, look at this one, a complete removal of the both axial ligand. If we are removing axial ligand along the z axis, okay, both axial ligand from z, the octahedral complex, now it has become the square planar complex. If you are removing the z axis and all the ligands along with z axis, then it will become what? It has now become square planar complex. Which of the following splitting patterns orbital energy does not on the scale? Okay, so we know that dx square y square will have the highest, followed by dxy. For dz square, I think this is correct. It was already given to you. That's what we are just making right now. A moment back, A is correct. So now we have the another important topic called as how to decide the stability of coordination compound. When we are talking about the stability, we are talking about their thermal stability. We are talking about the thermal stability of the complexes. Which of complex is more stable? So guys, it's very easy to explain, but before that, let me give you one example. So let us suppose this is a metal and one ligand is added over there, so that metal ligand has been formed there. This is called as K1. Ml plus L, this has become Ml2. This is called as K2. Ml2 plus L, K3. So if I want to calculate out, like if I add all of these together, then it will become metal plus 4 ligands give you Ml4. For this we defined beta. Okay, this will be given up as that beta 4, because 4 has been added there. Beta 4 is exactly equals to K1 into K2 into K3 into K4. That's it. There is one more thing called as K instability. K instability is the opposite of that, like how Ml4 will be dividing down into Mn4L. So K instability is actually 1 by beta 4. Learn it, that's it. We have now the another factor that decide the stability of complexes. The very first is actually the delta. So as I told you, delta stability is directly proportional to delta. Thermal stability is directly proportional to what? Delta. And delta T is lesser than delta O is lesser than delta square planar. Remember it. The another could be oxidation state. If there is a same oxidation state is there, different oxidation states are there, same number of ligands are there, then higher oxidation state will be having higher Z effective. Higher Z effective mean more stability. Z effective of the central atom will also be a deciding factor. Charge density of the strength of ligand is also a factor. We know that stability of the complexes with weak field ligand will be lesser stable than the complexes with strong field ligand. And then comes the chelation. Chelation is the tendency to form the cyclic ring. Let's try one question. Select the complex with the highest stability. This question came in JEE Main 2020. Select the stability with the highest beta n. So first of all, this is what? This is a square planar. This is what? Tetrahedral. No, this is also square planar. All of them are square planar here. But now the strength of ligand will decide everything, because all of them are, this is PT2 plus, PT2 plus, PT2 plus, PT2 plus. Now the only deciding factor out of these all is strength of ligand. So stability is directly proportional to the strength of ligand. So the correct answer should be A. Higher number of strong field ligands. Okay. Another question is, from the stability, hypothetical values have been given to us, predict the strong field ligand. So basically the stability is directly proportional to the strength of ligand. Because higher is the strength of ligand, more stable will be the complex. Stability is directly proportional to the strength of ligand. Applying that, higher value will be provided by B, 10 to the power 27. I think this is the correct answer. So till there we already have explained the applicative part of CFT, crystal field theory. Now crystal field theory is winded up, and now we have come to the another topic called as organometallic compound. We'll discuss organometallic compound in detail. We have plenty of more other topics then to handle it. Some of the questions from JEE 2025 as well. That's what we have to discuss with. How come we didn't see any of the questions from JEE 2025 here? I was adding those questions previously. Maybe those questions have been added to that series. Anyways, I have given top 50 questions right in the description itself, and in my upcoming class I will also explain you about the doubt discussion session will happen there. Some of the very important questions will be discussed as a PYQ over there. So please attend my tomorrow's lecture, that is already held on 11 a.m. morning. Okay, so do attend that. Unless, let's start organometallic compound. So what is organometallic compound? So guys, the name itself suggests organometallic compound is there is a metal and carbon bond is there. This is carbon of ligand, and this is a metal atom oblique ion. So whenever there is a direct bond of carbon and metal, these kind of compounds are called as organometallic compound. Just like TiOC4H9 is not organometallic compound because there is no direct bond of titanium and carbon. There could be three types of organometallic compounds which are containing metal and carbon bonds in the compound. There could be sigma bond, pi bond, and there could be sigma plus pi bond. Sigma bonded, pi bonded, and sigma plus pi bonded. Let's first start it from the sigma bonded complexes. Sigma bonded complexes are the one where there is a direct sigma bond. So let us say if I am having a compound like tetramethyl tin. So there is a bond of tin with methyl, and there is a sigma bond over there. That's why these are called as the sigma bonded complexes. Very simple one. Don't need to hesitate or need to overthink on that. These are very much beautiful complexes where pi electron density is useful in order to give you the this lone pair or the coordinate bond formation will be taking place by the pi electron density. So take this example, guys. We have bis benzene chromium, we have ferrocene with us, we have Zee's salt with us. These set of basically salts are, these compounds are called as the pi bonded complexes, because as you all can see, pi bond is responsible for the formation. And how are they written? They are written in very beautiful way. Like ferrocene, if you talk about it, is iron, eta 5, C5, H5 and whole twice. So this is how it is written. Eta represents in how many number of atoms the electron density is distributed, and C2H5 is the C5H5 is the formula of the ligand. So that's how it is represented. Like this benzene, we have chromium, eta 6, C6, H6. Please, it's clear. What should I tell? Eta is the number of electron density distributed in how many number of atoms. This is in 6. This will be eta 2. This is eta 5, eta 6, like that. Now the most important and the most useful and frequently asked kind of categories here, which is called as sigma plus pi complexes. These complexes are said to form the synergic bonding. They do synergic bonding, sigma plus pi bonding. If somewhere sigma plus pi bonding takes place, this bonding is called as synergic bonding. What is the synergic bonding? I'll explain you. We have to talk about the metal carbonyls first. These are some examples of sigma plus pi and CO2, CO8. I gave you an example at the initial of this lecture. Werner theory, Ian rule, so many places we use this example. We have another example of dimanganese decacarbonyl. So how this bonding takes place, let us understand that part. So it's very simple, guys. We have a metal atom with us with plenty of d orbitals surrounded by it, and not just d orbital, in fact the hybrid orbitals are also there. We also have carbon monoxide with us, C triple bond O, in which there are some set of molecular orbitals have been given over there. We'll try to explain what will be happening there. Try to understand. So initially carbon monoxide has what I must say, this is how we can explain it. There is an electron density like this. Metal also has something like this. This is electron which are donated. This is a sigma bond. This is a sigma bond. Now we also have electrons present in the these are pure d orbitals. This is the hybrid orbital. So now, and these are actually donated back into these are the anti-bonding molecular orbitals of carbon monoxide, ABMO, right? These are pi star molecular orbitals. So now we can see there are two types of things are happening. Two bonds are formed. Number one, sigma bond between bonding molecular orbital of carbon monoxide to hybrid orbital of metal, central atomic metal. First bond. Number two is the pi bond. Where is the pi bond is coming from? So guys, you all know that once these all orbitals are filled, these electron density can be shifted back to the carbonyl. So electrons from d orbitals of metal are given back to anti-bonding molecular orbital pi star of carbon monoxide. This is the way we say dual bonding is there, is sigma plus pi, and that makes it is called as synergic bonding, responsible for the strengthening of the bond. The bond of carbon and metal becomes very stronger. But what about the carbon oxygen bond? Now, since we all know the electrons right now which are coming, the going electron are from the bonding molecular orbital, the incoming electrons are incoming in the anti-bonding. If the number of electrons in anti-bonding increases, the bond order decreases. The bond order of which? Carbon oxygen? No, carbon and metal, the bond order will definitely increase because of the synergic bonding, double bonding. But because of the synergic bonding, carbon monoxide, this carbon oxygen bond will get weaker, and its bond order decreases because of the increase in the anti-bonding number of molecular orbitals. Anti-bonding electrons will be there, anti-bonding molecular orbital electrons will be there. So that's what we have to follow. Now let's see the consequences. These type of ligands are called as, guys, we call them pi acid or pi acceptor ligand. What do we call them? We call them pi acid or pi acceptor ligands. And the examples of these ligands are carbon monoxide, cyanide, nitrocilium, PF3, PR3, blah blah blah, etc. And this effect is called as synergic effect. Synergic effect means double bonding effect, sigma plus pi bonding effect. Consequences I have told you. Carbon and metal bond will be increased. Carbon and oxygen bond strength will be decreased. Also, the extent of synergic bonding depends upon the electron present in the central atom. Higher is the number of central atom, higher is the extent of synergic bonding. Let's say one question is there. The pi bonding is not involved in pi bonding, where we do not see pi bonding. So pi bonding is not found in Grignard region. With Grignard region, it is simply RMGX. So what is this RMGX? It's a sigma bond. Which of the following organometallic compound is both sigma plus pi? What do you think is the both sigma plus pi? So if any compound is both sigma and pi, it will be the one which is creating the ligand should be over there, pi acid ligand. Which of the following organometallic compound is both sigma plus pi? Ferrocene? No, it's just pi. This is pi. This is only sigma. No, metal carbonyl is there. No, this is sigma plus pi. Pi acid, and this is only sigma. So what should be the correct answer? Of course, C. So let it be CO, NO, CN, etc. Ligands are there. They all do sigma plus pi. That is what we call as synergic bonding. Which of the following is not true? Is not true for the metal carbonyls. That oxidation state of central atom in the carbonyl is 0, which is true, because if it is carbonyl with no charge, then metal atom will also be having no charge. D pi p pi back bonding takes place. D pi from the central atom, p pi is of this, but it is not p pi, it actually p pi star. So this is actually the correct answer, and this is true. Pi star molecular orbital, pi star is anti-bonding molecular orbital, and bond order of CO decreases. This is also true. This is also true. So everything is true, only B is not true. I remember this question came in which year I don't know, but it came in some year. Okay, like this question came in JEE Main 2022. It's all about the metal carbonyls only. The metal carbonyl question is very simple. Number of complexes which will exhibit a synergic bonding among the chromium hexacarbonyl, manganese pentacarbonyl, and Mn2CO10. So I think number of complexes which will exhibit synergic bonding. See, it is all because of CO. What is this CO? CO is the pi acid ligand. If there is a pi acid ligand, all three will do the synergic bonding. The answer should be 3. Another question, the carbonyl complex is zup. First of all, we must know the structure of this compound. Until unless you know the structure of this compound, you cannot comment upon rest of the things. There is a CO over there, CO over there, CO. Now you find out what has been asked. Number of CO bond, which is 1 plus this is X. Terminal ligands are how many? 1, 2, 3, 4, 5, 6. 6 are there, which is actually Y. So X plus Y will be 7. 7 is the correct answer. So that's it, guys. Let's take a break for a while, and then we'll come back and connect back on this topic called as isomerism. So allow me a moment for a while, and I'll be shortly joining you back. So that's, now we have the final part of this chapter, which is isomerism, and right after isomerism this chapter will be over. I have already shared a list of some very good 50-60 questions that you can try from your end. As I can see in the description, it is given. In the description you can find out class notes link is there, Telegram channel is there. Please go ahead with that. And 50 questions of this also are there. 50 questions of triple R coordinates compound is there. Please go that, and please go there and try to solve these question 50. And in tomorrow's session we'll come up with the doubt solving and these questions of all. Okay, let me allow me a moment, guys. डिस्क्रिप्शन में तो 50 क्वेश्चन का लिंक है, क्लास का लिंक अलग से दोनों, मैंने उसको अभी डाउनलोड करवाया ना, 50 क्वेश्चन को भी डाउनलोड करना चाहिए उसमें। क्लास में तो जब बच्चा जाएगा तब दिखेगा ना ये किस किस का लिंक देखो। पहला जाएगा नहीं 50 क्वेश्चन ऑफ ट्रिपल आर, 50 क्वेश्चन थोड़ी है ये 50 क्वेश्चन है, डॉक्यूमेंट है, 50 क्वेश्चन है। फिर क्लास का लिंक है, क्लास लिंक भेज दिया था मैंने, देखो अरे मैंने सर एक बार भी डाल दो अभी कभी, मैंने बोल दिया कि बच्चों को पिंग भी कर देना कमेंट में डाल के। देखो सर क्लास लिंक देखो, ये सर अनअकैडमी क्लास देखो 19 को टॉप 50 क्वेश्चन की क्लास का लिंक है, ये तो डाला होगा नहीं सर, जो हमने डाला होता है क्या है वो ये है 50 क्वेश्चन आपने डाला, ये मैं डाल देता हूं, अभी डाल दो, मैंने बोल दिया बच्चों को पिन बस कर दो, अभी कर देता हूं। So guys, I have asked to give you the class link, will be surely updated in the description itself, and also it will be commented and it will be in the pinned comment. Okay, so you can pick the class link and can start your work accordingly. Now let me take you to the types of isomerism. So there are like you all know what is isomerism. In organic chemistry we also study this term called as isomerism. Isomerism is the property of the compounds which have the same molecular formula but different properties, physical and chemical properties are different, and there could be broadly two type of isomerism. One of them is called as optical isomerism, structural and stereo. Structural isomerism is based upon the different connectivity, connectivity structure based basically differences are there in two compound. When stereo, there is a relative position is being changed, and maybe it could be optical, it could be geometrical also. Anyways, let me take you to structural first of all. So this is the structural isomerism definition given to us, not required, which is actually because of the chemical linkages and distributions of the ligands inside and outside of the sphere. The very first one is called as isomerism. This is your ionization isomerism. So in ionization isomerism, if there is a complex and we dissolve in the aqueous solution and we make its aqueous solution, the number of ions will be different. Anyways, what is this here? Ligand becomes counter and it was anyways, this should not be an arrow, it is just representing these two are the ionization isomers of each other. Because if I okay, this is converted over there into this, I think this is a potential ligand, Br negative acting as a potential ligand and replacing sulfate from here, displacement is taking place. So if you dissolve it in water, the number of ions will be different. The number of ions are, one of the complex ion will be containing sulfate ion in between of the complex, and Br negative will be coming out of this along with a positive charge over here. This is also aqueous, this is also aqueous. And then if you talk about this one on dissolving in water, the nature of the complexes you can find, the type of the complexes are entirely different. This is having bromine ion which is coordinated with the cobalt 3 positive, and sulfate ions is coming as the ionization sphere, coming in the ionization part, right? This is the differences. So the differences arises when the different number of ions are appeared in dissolution of water, then it becomes ionization isomerism. The property is called as ionization isomer, and these two compounds which are different in the number of the different ions they are producing in after their hydration or after dissolving in water, making their aqueous solution. Number 2 is called as hydration isomerism. Hydration, name itself suggests hydration means water. We are right now talking about hydro means water. Anyways, this hydration, water number of water molecules are different as coordinated and as a counter sphere. Now, you might be getting what I'm trying to say, but if not, let me just re-explain this part to you. Let us suppose we have this complex, this chromium H2O4 Cl2 Cl2H2O. Let's suppose this is how it is written: CrH2O whole 6 and Cl3. This is a complex. This is the basically molecular formula of the complex. From this I can prepare 2 or 3 or many kind of complexes, applying how many number of water molecules can form the coordinate bond with chromium 3+ ion here. So let us suppose there are 4 number of this. Cl2 is this, 1 Cl is this, then the rest 2 H2O should be written outside of this box as a counter sphere. Similarly, if 3 number of H2O I'm using here, 3 Cl3 are here, then definitely 3 water will be there in outer sphere. So these two are different in the number of water molecules inside and outside of the coordination sphere. This type of isomerism is called as hydration isomerism or solvation isomerism also, if any other solvent is used. Just like water, if I take ammonia and ammonia is taking or working as a solvent also, then this way it will be called as ammoniated isomerism or ammoniation isomerism, or we can simply call it hydration isomerism, solution isomerism, solvation isomerism. There are some examples. So as we all can see that as the number of water molecules are increasing, the color from dark green is increasing its intensity from gray green to violet. I remember one of the question in JEE 2025 has come on the same thing, which probably I'll be solving with you. It's given in my today's DPP that I have shared with you with our 50 questions that I'll be dealing in tomorrow's session. My special session will be arranged there on Unacademy application where we'll be solving all of these questions. Okay, so don't forget to attend this lecture. We have next structural isomerism. We have next coordination isomerism, called as third type of isomerism is coordination isomerism. What happens in coordination? This type of isomerism takes place whenever positively charged and negatively charged species, both of them are complexes. So like cation and anion both are complexes. If cation and anion both are complexes, then their central atom will be exchanged. In order to exchange their central atom, actually cation will be exchanged to anion and anion will be exchanged to cation. This is how it works. But we say that there is an interchange of ligand. We usually say there is an interchange of ligands between the cationic and anionic part. But if the ligands have been changed, the cation and anionic part will also be changed. Like here, cyanide has a -1 charge, ammonia has 0 charge. Charge on chromium is +3. This is cation. But once you exchange the CN over here and bring NH3 over here, this cobalt will become +3. Overall species will become +3. This will come as a cation. See, this is cation now, this is anion. So that is what it happens. Usually I can simply say that central atom is exchanged. In short, we can say that central atom is exchanged between two complex cation and anion species. Then we have other examples also, but again the similar example you will find both of the species will be complex, and then we can identify this different type of isomerism called as coordination. There is one more type of isomerism called as linkage isomerism, and linkage isomerism takes place wherever there is an ambidentate type of ligand is there. There is an ambidentate type of ligand is there. So let's say if nitro has been attached over there, it has yellow color. If ONO is there, then it is red color. But in nitro, connection is with nitrogen, central atom is attached to nitrogen, here it is attached to oxygen. It's very simple, guys. We just need to identify what has been given in the question, what compound has been given, what is the possibility of this kind of compound with the isomerism. So Earlier, like if both cationic and anionic species are given as complex, in that way we can simply say that yes, this is a coordination. There is a possibility of coordination isomerism. If we see any ambidentated ligand is there, then we can simply say that yes, sir, over here there's a possibility of linkage isomerism. There is one more thing called as the ligand isomerism. However, this is very rare. This is very rare, and this has not been even given in the NCERT, and this is not in our syllabus. But we'll just cover it anyhow. It simply says that if ligand itself has a isomerism in it, like ligand has a molecular formula as the same, but different connectivity might be there. Let's suppose this example is there. So this is 1,3-diamine propane. In this 1,3-diamino propane, 1,3 positions are required with the donor atom of nitrogen. But if we talk about the same for the another 1 and 2 position, if you make it, because 1,2-diamino propane, so this is over here. So this is a 1,2 position, that was a 1,3 position. So this is the difference and called as the ligand isomerism. Not so common, but yes, we can take an idea about it. There's one more called as coordination position isomerism, but this takes place in the bridged complexes only. This doesn't take place in regular geometry, regular coordination compound. It takes place in bridged complexes only. This type of isomerism takes place in bridged complexes. So in the polynuclear complex, polynuclear means bridged complexes only, and there is an interchange of the ligands. So there is an interchange of the groups which are present over here. Let's say this is NH3,4, this is NH2Cl2. Let's say if I make it 3,3 in both sides, although this is a symmetric, this is unsymmetric, but these two have same molecular formula. These two are called as the coordination position. Now I don't think there is any doubt in as such. If we talk about the structural isomerism, all the 6 parts that we have studied, structural isomerism, which we have gone through, like one of them was ionization, another one we had linkage, then solvated or hydrated isomerism, coordination isomerism, coordination position isomerism, and ligand isomerism. 6 kind of categories we have studied till now. I don't think there should be any doubt. Let's try to solve some questions from it. We have a question from JEE Main 2021, a question that was asked in JEE Main 2021. Let's try this question, everyone. Let's try this question. The question is simple and says that there's a list of compounds and what kind of isomerism do they show. You all know what is this. There is a double complex, cation and anion both are complex, can be exchanged together. This is called as coordination isomerism. Now which else does it show? It has cyanide, so it can also show linkage because of the cyanide. Cyanide can become isocyanide somewhere. Formula will be the same, compound will be entirely different. Then we have cobalt, NH3 whole thrice and NO2, but NO2 will definitely go under linkage. And then we have CrH2O6Cl3. This will be giving you solvate isomerism because of the water molecules present over there. So can we identify the correct answer from here? A is matched with 1 and 3. B is matched with just 1. C is matched with 3. I think A should be the correct answer. Then we have right after structural isomerism, we have stereoisomerism. Name itself suggests stereoisomerism. The differences of the groups in space we can't identify as a structure to them, but we can identify them in spatial arrangement. They might be having different physical properties. They might be having different chemical properties as well, and their reaction towards the plane polarized light might differ. Some of the, you know what, this is exactly the same that we study in organic chemistry, optical isomerism. They are like non-superimposable mirror images of each other. They can show you a deflection of the light in opposite angles, and a dextrorotatory, levorotatory, exactly like that. So I'll first of all take you to the geometrical isomers, and for that, geometrical and optical, believe me, this is the only part of this chapter which I am not giving a very detailed analysis, because the reason is pretty same. It doesn't require, very honestly saying, this doesn't require. Just take an idea, how does it look like and appear. Just learn it, try to take an idea in your mind, and you will be superbly doing it. Let us suppose, first of all, we started from the geometrical isomerism only. The geometrical isomerism, you all know what is geometrical isomerism, and we usually study in 2 ways. Tetrahedral geometrical will not show by tetrahedral geometry, because tetrahedral complexes always have a plane of symmetry. No, yeah, not plane of symmetry. Sorry. Oppositely said. A tetrahedral species which is having 4 different groups out of it will definitely be optically active, but not geometrically active, because geometrically all the relative positions are the same. You cannot exchange the groups by just differing the number of atoms. So let's say we go for Ma6, no Gi, no Mi. Ma5b, it doesn't also have anything. If we talk about the Ma2b4, A2b4 means two A groups are there, so these A2 groups could be adjacent to each other, then it becomes cis, and if they go opposite to each other, then it becomes trans. So cis and trans, there will be two geometrical isomers, but that has no enantiomers. Ma4bc, no enantiomer, but only geometrical. Ma3b3, it is said to have two type of isomers, FAC plus MER, facial meridional. Ma3bc, b2c, to learn it, man, no idea on how many things are being there. And similarly, it starts with the number of enantiomer also. Wherever it is said that number of enantiomer is 1, that means it's an optically active compound. No, the only atom, the only species that exists and doesn't have any plane of symmetry, any element of symmetry, and it's an optically active, it has one number of enantiomer. Then 2 enantiomers are there, D plus L, 6 enantiomers are there for M, A, 2, B, C, D, E. Like that you can form. Just take an idea and just try to learn all of them. This is more important part of this chapter. Just take an idea and just learn them, okay? Don't you unnecessarily go in very depth of this part and unnecessarily making chaos for you. Simply take an idea and move forward. Like AA, whatever it is written there, it's a symmetric bidentate ligand. Symmetric bidentate ligand binds through two atoms, right? Like AA3 is there, so there is no geometrical isomerism will be there. Number of enantiomer is 1. Like what's the meaning of number of enantiomer as 1? What does this mean? In fact, one enantiomer is there. Like only one compound exists, which might, but if it is optically active, there will be like 2 variations possible in it. Okay, we'll see. So number of enantiomer might be saying that after these two, only one is optically active. Only one is optically active out of these two. That's what it meant to say. Now what is this AB? That AA was a symmetric ligand, bidentate. This is a bidentate ligand, but it's asymmetric, like glycinate ion. One of the donor atom is oxygen, another is nitrogen. So whatever it belongs to, whatever it attached to, it's a different atom there. So out of these two, number of GI2, both of them will be optically active. Enantiomers also optically active. Out of these 5, 3 will be optically active. 6 out of 5 will be optically active. Blah blah blah. Like that, it has been given to us. Let us try some questions. The list is with you. You can download the notes from the link given in the description. Our Telegram channel has been there, but just join it and you will be getting your notes over there. Unless then, let's try solving some of the questions. Which of the following complexes species is not expected to exhibit the optical? Which of them will not exhibit optical isomerism? Because I know Ma3B3 only does GI, no OI. And how many GI are there? Facial. Let me reveal how is the facial made. They will acquire a face. So this is your chlorine. This is one chlorine. This is another chlorine. So this is like that. Let's say this is coming out of the board, and in our side this is your Cl negative. Let's say this is another Cl negative going inside, and this is NH3. This is another NH3. So if I connect them and connect them well to know what does it look like. So what is this, by the way? So this is actually Can you check it out? This is actually representing a face of this, and that's why we call it facial or FAC. Okay, only GIR FAC plus MER. FAC bole to facial, MER bole to meridional. Let us try the another one. We have CO3 plus and one Cl being here, another Cl being here, and one Cl being over here, and this is your NH3. NH3, 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 and then we have ClCl. So, man, how many NH3 is Cl? So just take an example, everyone. Let us look at this. This is actually covering the mid of this molecule. How? Take one Cl, connect it to another Cl. This is another Cl, and this is connected over here also. So we are now cutting this molecule into this, and this is actually meridian. This is actually you can check it out like this. Like that. This is cutting between. So this is called as meridian, and the name of this isomer is meridional. So one of them is facial, another one is called as meridional, and there is none of them is optically active. Always remember this part. Let's see the another question. We have cobalt En2Cl2 positive and cis1 is also there available. The correct statement regarding them is what? So the correct statement about them is what? Okay, so see, if you draw the cis isomer of this, see this is where we can connect the En with, and this is where we can connect the En with. This is your Cl, this is Cl. So this is actually trans isomer. This is the trans form of this isomer, and it has a plane of symmetry. So if I cut it like this, it has a plane of symmetry. So that's why it is optically inactive. But let's say if we are talking about its cis form, let's try to draw its cis form. This is cobalt, cis. How does this cis form look like? Like this, and like this. So if you draw the cis form, then there is no plane of symmetry, and even if you will observe its non-superimposable mirror image, this is CO, this is En, this is another En, and this is one more En. So this is the, we can say this is optically active. The cis form is active. So which one this is form? A is trans, so A is inactive. So A क्या बोल रहा है? B can be active, A cannot be. D is correct. This was the question from JEE Main 2020. Let's see another question. Again, it's a structural isomerism question. Structural isomerism based question. We have first molecule over here. Both of them are coordinated. Both of them are complexes. We'll say coordination isomerism. Exchange can be done between the central atom. Then we have nitro group over here. Nitro can definitely go for linkage. Water molecule can go for solvate. Oxalate is there. Cis is there. Cis can be showing optical isomerism. So this is the correct answer, guys. Can you match it properly? A with 3, A with 3, B with 1. A with 3, B with 1. A with 3, B with 1. Only one option is there, B. So that was a question in JEE Main 2021. How easy was this question? Let's take another question. The total number of stereo, geometrical plus optical of this ion are. Total stereo of geometrical and optical we have to tell. Okay. So first of all, this is another MA3B3 type question. MA3B3. So only GI. What GI? Facial, meridional, and no optical isomerism. So only two answer is there. A. Number of geometrical isomerism found in the metal complexes respectively are. So number of geometrical isomerism we have to tell them. Let us look at the question. CT, PT, it is a square planar, by the way, square planar. It can show you cis trans, so it is 2. This is a tetrahedral. No GI, no OI. Ruhenium 3,3. This is a octahedral, but this has facial plus meridional. Just like it had cis trans, it has FACMER, and this one, the last one, it also has a cis plus trans, and this is an octahedral species. So again, this is be having 2. So 2 plus 2, so 2012 is the correct answer. 2022. 2022 is C. C is the correct answer. Now check out some of the importance of these compounds. That coordination compounds are widely used in the qualitative and quantitative analysis, like estimation of water. I remember like nickel 2 plus ion can be identified using DMG whole twice. A complex is there, the neutral complex, and so this is a red color complex. So this is a very important complex, by the way. Estimation of hardness of water is used into. Extraction processes of gold and silver, we call it cyanide process, where the complexes of gold and cyanide silver are made. Purification of metal, it is used into. Biological importance, that vitamin B2 chlorophyll is made up of Mg2 positive. Vitamin B2 contains CO3 plus. Hemoglobin contains iron 2 plus complex. These all are the complexes. Industrial importance, Wilkinson catalyst is there. Forgot it. What is Wilkinson catalyst? Wilkinson catalyst, I think that is the Wilkinson catalyst only, that rhodium, and we have PPH3, black and white photography we use silver complex. Chelate therapy, cisplatin, you already know about cisplatin. PTCl2NH3 whole twice, cisplatin. So yes, you have to remember the formulas, whatever it is there. These are important one, and I think that's it. I think let's try some questions and then we'll wind up the session. So there is a question: which of the following is considered to be an anti-cancer? Cisplatin. This is the formula of cisplatin, as I told you. Wilkinson catalyst is used in polymerization. Rhodium complex, I told you. Now the same question has come over here. See, cobalt, vitamin B12, I told you. Rhodium, Wilkinson catalyst. Zinc is used in carbonic anhydrase, in which acetic acid, like acid is converted into carbon monoxide and CO2, I guess, somewhere like that. Exactly idea on that. Magnesium is chlorophyll, so this is how you can pick the correct answer. So A3, B4, C1, I think this is the correct answer, C. Hopefully this was enough for all of you, and if you need some more practice, please join my tomorrow's lecture. Tomorrow's lecture is going to be even more important for all of us. Please join that session tomorrow at 11 AM. It has been scheduled, and more details will be available on our description itself. Please join the lecture on time, and we'll practice over there. Any doubt is there, please come with your doubts, and after solving the 50 plus questions that I have provided already in the description, there are some top 50 questions that you have to do by your own, that will make you more comfortable in your upcoming JEE attempt of 2025. Bye bye everyone, take care. Oh yeah. I forgot to make one more announcement over here. I forgot to make the one more announcement over here. The announcement pretty simple. It simply says that we Unacademy, the team of Unacademy, is bringing a very amazing surprise for all of you. I will not reveal the name, what is it exactly, but every year we conduct this event in order to beneficiate all the students throughout India, they are wherever they are studying from. So right guys, this is your JEE Nexus by Unacademy. This is our channel, JEE Nexus by Unacademy, our Unacademy's official channel, where on the home screen you can find live in 11 days the biggest event, and this is the biggest e-revolution guys. Please go and click on the notify button, and that's it. Okay, so bye bye everyone.